Good morning, everyone. So I'd like to really thank the organizers for setting up this summer school. A few years ago, I myself organized a few summer schools, and I know it's a lot of work. And I hope you enjoy the week as much I do. So today I will be talking about optimal transport. So the title, I'm going to parse it with you. It's about theory, a bit of algorithms, and applications to single-cell omics. Optimal transport, for those of you who've never heard this word, is a very important theory in mathematics that has been under the spotlight in recent years, in particular because two mathematicians got a Fields Medal for their work in this theory, Cédric Villani and Alessio Figali. But recently, we've seen a lot of developments happening in the field of machine learning, and some exciting developments that echo a bit or are a bit in parallel to those that you might have seen in, diffusion models or conditional or continuous normalizing flows, etc. So to introduce the subject, I think it's easiest to start with a puzzle, and I hope this puzzle will give you a bit of intuition about what we will try to do during the next 3 hours, and how we will generalize this puzzle during the next 3 hours. So imagine you enter a room, the light is off, okay? So you turn on the light switch, and you see 6 points, 6 particles. I'm going to be very generic, those are 6 things in some configuration. And I'm looking at them, and just right at that moment, someone turns off the light again. And so I'm rushed, to turn on the light again to see what happened with the particles. And so the particles now have moved, and they are in a different configuration. And I would like to understand what happened during that moment, when I was not able to observe them. And of course, you can generalize this to a more, I would say, generic scientific process where you have measurements before and after something happens, and you want to be able to reconstruct a possible way the particles that were in this left configuration landed in this right configuration. So to make things simple, I'm going to basically label them with 2 different colors, blue and yellow. And I'm asking myself the question, who went where? And this, of course, is a very ill-posed problem because there's many ways you could reconstruct the trajectories that moved the blue particles to the yellow particles. And so we need to have some notion of bias, an idea of, trying to promote better, more likely solutions. And so very likely solutions, of course, would be those that minimize the notion of energy in the sense that they go through straight lines. If I'm assuming, for instance, that this particle went there, maybe in the absence of any other knowledge, it might be a good bias to believe that, it went in a straight line. Now, if I start assuming that, the particles move in straight lines, then the question is, what happens, basically? Which one goes where? And in this case, I'm asking yourself, how many possible ways do you think I could come up with where each of the blue particles goes to each of the yellow particles? I'm hearing the right answer, not the number, but yeah, please go ahead. Yeah, so it's 720, which is 6 factorial, exactly. There's basically 720 possible permutations where each of this blue point can go to each of those, either of those 6, etc., etc. So it's going to be 6 choices, 5 choices for the second particle, 4 choices, 3, 2, and just 1, the remaining particle there. So immediately you see that this problem, which is quite trivial, is actually is combinatorial in flavor. So what people call the optimal transport is going to be among all those possible configurations, basically, or assignments or matchings, the one that has the least possible energy that is wasted. And so here by energy, I mean basically that I will be defining a cost between 2 particles. So I will be considering a length of this segment, or maybe the square of that length if I want to use a square Euclidean distance, or any other more exotic function. And we will see that we will encounter such functions. And I will simply say, well, it turns out that this one is the one where if I use, for instance, the distance, just the plain distance, it seems that this is the one that is the cheapest to move the blue particles to the yellow ones. So this is, if you want, the V0.0 optimal transport. This is the one that people were discussing in the 60s, 50s, when they were talking about optimal assignments. The one that we will be trying to do is a bit more than that. So the first thing, you have probably heard about optimal transport under a different name, which is this notion of Wasserstein distance. So the Wasserstein distance is going to be that best possible, sum of length of segments. And it's used a lot, regardless of, the motivation that I gave here about seeing something after or before, as simply a way to compute the distance between two configurations of points. And we will see it's a bit more general. It can handle different numbers of points, different masses, so it's more versatile than what I'm just showing here. The other big task, I would say, in optimal transport, which has been on the radar of mathematicians for 2 or 3 decades, but which is now used a lot in machine learning, is the notion of extensions of this, those green lines out of sample. So I gave you a configuration before, I gave you a configuration after. I have this, intuition that the particles are moving somewhat in this way. Can I come up with a principal method to estimate this map out of sample? And I would say this is a bit of one of the frontiers, right now in optimal transport research. This is what people are focusing on, and I will be presenting a few results in that sense. So to summarize, when you are using only samples and you're only trying to compute matchings, we are going to be solving discrete optimization problems, which can be relaxed to let's say, convex optimization problems. When we will be talking about extending things out of sample, this will be more a functional perspective. And so here we will be talking about, let's say, those are samples that are sample IID from 2 distributions. How can I recover such an operator? So in the next slide, I will try to give you a brief survey of the current challenges. Don't worry too much if part of the math or the algorithms is not super clear. I want to give you like a 20-minute survey of what's going on right now in the community. So starting again with basics, the permutation problem. Okay, I have 5 points, so 2-point clouds of the same size, a cost function that basically helps me figure out how far 2 points are. So you can think of this, for instance, as there are 5 customers somewhere in the city. There are 5 taxis right now that are idle. They don't know where to go. The 5 customers call the taxis. The company has to dispatch the drivers. What is the best possible way to send them? So of course, one solution is just one of those permutations. And if you score, I'm going to be a bit more specific here. If you score the permutation as being the sum of the cost between the point and the corresponding taxi, y sigma I, then you have a criterion and you want to minimize that criterion. And the sum of the length of that criteria is basically just simply this thing. So the sum of the length of those arcs is this thing. So there's, of course, as we just mentioned a few minutes ago, there's 5 factorial possible permutations, but I would like to insist on what does not constitute optimal transport. So sometimes it's easier to define something by insisting on what it is not. And in this case, I'm sure you've all used some form of assignment before that involved nearest neighbors. If you just give me 2-point clouds and you ask me to assign, let's say, the points of the first point cloud to the second point cloud, the easiest by far is to do a nearest neighbor match, basically. So you would basically match every red point to its closest blue point. So the nice thing about this is that this goes very quickly. I just need to compute the distance between every red point to every blue point, or using other algorithmic tricks, sometimes they can go a bit faster. But once you do that, what you cannot ensure is that every blue point will be selected only once and only once. Of course, this is what's going on. We have this kind of degenerate matching. So here, I'd like to emphasize a bit the difference, the conceptual difference between optimal transport matchings, which are really one-to-one, and I would say nearest neighbor matching, which can very easily collapse. And so in many applications, we will frequently see a bit of this tension. I will show later that there is a way to somewhat interpolate between the two. But sometimes, maybe optimal transport is not so useful and you're very happy with a simple nearest neighbor match. But sometimes, actually, you feel that you're losing something in the process of discretizing or quantizing, let's say, the two measures by just using nearest neighbor matches. Because somewhat, you're not using those points here. And so if you are in some learning process, where you want to quantize efficiently those points onto another basis, then maybe you're going to drop points all of a sudden. So this introduces all sorts of issues. So this is an important, I think, distinction to consider. Now, let's go back to just simply minimizing the... Oh, by the way, yeah, I want to insist that you can ask questions anytime. Please feel free to raise your hand, and I will be very happy to be interrupted. So the one that we will be seeking is this, sigma star. And so the question is basically, how do we get this to this sigma star? I'm sure many in the room here know this because this is one of the elementary algorithms that are taught in CS 101, and this is basically going to be a question of computing. Solving it with the Hungarian algorithm. Before I actually get there, I wanted to say that there are other cases that people have been exploring in applications, and one of them is simply to use this as a task assignment. It's like an operations research task of trying to figure out what are the links between what is the best possible way to link a red point to another blue point. And similarly, as I was saying before, it's a very typical measure of dissimilarity between point clouds. So as I was just saying, the canonical way to solve this problem is arguably the Hungarian algorithm, which was proposed independently by König and Egervary in the early 20th century, and was highlighted by Kuhn again in the early 50s. And so as you can see, this is already quite a heavy-duty algorithm because it's cubic in the number n. So it's not n factorial. We don't need to explore all of the permutations, but it's still very costly. So beyond this computational issue, there are a few major flaws of this optimal permutation problem or optimal assignment problem. And the very first one that comes to mind is that this doesn't work if you're comparing two probability distributions or 2 point clouds, let's say, of different sizes. So if I throw in, some y6, all of a sudden you're a bit stuck, and you don't know what to do with the 6 point. And so you can start thinking about ways of, selecting 5 points among the 6 and discarding 1, but it's not very clean. The other problem is that this is not going to provide at all, the out-of-sample extensions that we had in mind, which we will need in some applications. So when I give you, this optimal matching, it's not going to be easy to come up with a function that will send, this new point. And the last part is, as I was mentioning, the computational cost. Cubic, of course, is way too much for applications in ML. So because this is all very constrained and smells a lot of, discrete optimization, combinatorial optimization, we're going to move away from this model and use what people could call a relaxed matching. So this is work that dates to the 40s. This is a Russian mathematician, Leonid Kantorovich, and Americans, Hitchcock and Koopmans. And what they proposed is the following. They said, if now you give me two probability distributions, 2 point clouds which are weighted, that do not necessarily contain the same number of points, but that has the same total mass. So let me be a bit more explicit about this. By this notation A1 delta x1, I am basically saying that there is a square at x1. So this is the notion of a Dirac mass at x1. And there is a mass of A1 on that square. So the area, if you want, of the square is basically equal to A1. And so in that sense, we will try to get inspiration from this optimal permutation problem. But you can see already that things don't really compile, because if I assign, let's say, this point to this point, but then the mass is not sufficient. If I assign this point to this point, there is too much mass. And so I need to have something that is a bit more relaxed, a bit more flexible to account for this problem. And so what we will use is what people call an optimal transport matrix. So instead of having a permutation, which is a discrete object of integers, we are going to parameterize permutations are matrices and generalize those permutation matrices as transport matrices. So what is the idea? Well, you just collect all of the masses, of those red points. Similarly, you collect all of the masses of the blue points. So again, the assumption here is that the total sum of the red squares is equal to the total sum of the blue squares. And I am going to come up with a matrix which will have as many rows as red points and as many columns as blue points. And from there, I will start creating a transportation plan. So really have to think about, as if I was transporting some mass, from this point here to this point here. And by taking a chunk of the mass in this weighted Dirac here, I am assigning it to this point here, y3. So which means that the second point here is taking a bit of its mass here and assigning it to this point. And of course, I haven't done the job of actually getting all of the mass that I need there, but I already started, And now I need to have a bit of mass here that remains. Where should I send it? Well, maybe I'm going to send it from the second point to the fourth point, and this is the little bit that I had left. And so now, let's do this a bit heuristically. It's always quite easy to do this heuristically, actually, to come up with, let's add, and then the surplus, try to fill up it in somewhere else. And so what you start up here is seeing is basically squares that pop up, and that assign the mass. And what I'm also trying to keep track of here is that the width of the arrow should match here more or less, of course, with the amount of mass that is transported. And so if you do this, there's three constraints that we need to have for this matrix P. First, this matrix P must be non-negative. If I'm keeping track of how much mass is sent from one of the red points to one of the blue points, then the entries need to be non-negative. That's quite natural. The second thing is that if this row here denotes all of the mass that is leaving this red point here, there were two branches here, then the sum of those two areas here should be equal to this one. This is what people call a mass conservation principle. And this is, if you think about it intuitively, what is the big difference with nearest neighbors, and this is where basically the constraint of optimal transport arises. And the same thing happens here, where you want to have the amount of mass that arrives to the blue square. And so in algebraic notation, P is a matrix that is non-negative elements. P times 1 is going to give you the row sums, and P transpose times 1 is going to give you the column sums. Now, as I was saying, the most famous mathematicians for this are Kantorovich and Koopmans, because they both received the Nobel Prize in economics for this model in the 70s. And I would say the backstory of this was proposed essentially during World War II, where you can obviously see some logistic interpretation for this problem. Imagine that I have some, resources or soldiers that are somewhere on this map, and I want them to be in another location on the map. If I am the one that is actually controlling the army, it's in my interest, of course, to get from this red configuration with weights everywhere to the blue configuration as fast as possible. Of course, this can apply also to gas. Let's say, I need gas to power my army. Anything. Whenever you have a centralized economy, that is able to take all of the decisions of who sends mass or goods where, then you are in the position to optimize things. And so Kantorovich was really interested in maths of industrial processes, and of course got more interested in this during the war. And it was the same for Koopmans. And so all of this is really very much, owing to the war efforts that all of a sudden shifted completely from let's say, more disorganized economies to very centralized ones. And it's also interesting to see that the Soviet Union, actually earlier in history, in the 30s, was already looking at this kind of problem through another mathematician called Tolstoy. So now the cost that we will be defining is this cost of P. It is going to be just simply the very natural extension of the permutations cost that we have. We're going to sum the amount of mass that goes from I to j. So here it's not going to be a binary, 1 or 0. It's just going to be Pij, how much this one is sending there, times this cost function. So here again, for intuition, I'm assuming it's the distance. And if you look at this, you still have the same intuition in terms of length of arrows, except that this time the arrows are weighted by area. So it's as if you were looking at the area. So here this arrow has basically a length, which is the cost, and a width, which is the amount of mass. So you just compute the sum of the areas of those arrows, and you get the objective. And of course, here the goal, as usual, is to find the best possible P star that gives you this optimal transportation matrix. So this optimal transport problem is really one of the canonical optimization problems. So if you open an optimization textbook, it's very likely that it will be quoted in the first pages, or maybe the first chapters at least, of the book. And in particular, it is a canonical linear program, which is a subset of convex optimization, which was explored historically earlier. And we owe it to Danzig to find a solution to this problem. And actually, historically, it's really Koopmans, the American Dutch mathematician, who submitted to Danzig this problem. Danzig realized that this optimal transportation problem was a subcase, a particular case of linear programs that he was working on, and that his methods could actually work well to solve this. So why is this a linear problem or linear program? Well, if you think about this, this is a variable that has nm variables. It's a matrix. This is a linear function of P. That's fairly obvious. It's just a dot product sum of Pij cost of xi yj. And there are linear constraints. There is the constraint that the sum of the rows of P are equal to A, the sum of the columns of P are equal to B, and there is non-negativity constraint, which is just an inequality constraint. So polyhedral, if you want, constraint. This is a linear program which is in the so-called standard form. So it's really, a very orthodox way of, setting a linear program. And so we can use some of the algorithms that Danzig proposed. The great thing is that as far as linear program goes, this is a very well understood field by now. This is a fairly efficient family, let's say, of solvers. Of course, those are all worst case complexities. So this is to show how many iterations you would need following, the various recipes that are in Danzig's network simplex approach. The bad thing is that for machine learning, of course, if I am telling you again that I'm in a cubic regime, so this is cubic because it's going to be nm times whatever n plus m with a log, so it's super cubic. This is, of course, way too much. Okay. So one of the things that I will be introducing is a slight variant of this problem, where instead of computing a linear program, we are going to solve a regularized linear program. And this becomes a convex problem. And so this term here is the entropy of the coupling matrix P. So remember that because the matrix P has row sums A and column sums B, in particular, the entire sum of the matrix is equal to 1. So this is a coupling matrix. And so you can write its entropy. It's just going to be Pij log Pij summed over I and j. And it turns out that, and I will detail a bit this helps you go significantly faster. you can compute a regularized solution that is a lot, I mean, that basically has quadratic time. And one of the side effects of adding this regularization is that you will see a bit of, how can I say, blurring or smearing, where you're going to see some added connections between the points. If you just follow a linear program, typically the transportation matrix is very sparse, whereas if you add this entropy, you will see something that is a bit more vague. So this has powered a lot of the advances in optimal transfer for machine learning in recent years. And there's another one that I'd like to highlight, which is a bit newer, which is so-called low-rank approaches. So in the previous, in the entropic regularization approach, we throw in some regularizer. In this low-rank approach that I've been developing with Meyer Sedbon and Gabriel Perret, what we have is we are going to impose a non-negative rank on P, and I will show you later that this yields much faster computations to the extent that there are, yes?
Can I have a question?
Yes.
Do we have any, I don't know, theoretical assumptions or algorithms to define the perfect R for this problem?
Oh, no. I will go a bit more into the details, but if I can say, I mean, answer very briefly with an analogy, it's really very much like the K in K-means. Okay. It's, you can follow some simple rules of thumb to set R, but there's no theory so far. Okay. You're welcome. So I will be discussing this as well, but just on your map, know that we can now solve something that looks like, optimal matching problems at a scale that is, let's say, hundreds of thousands of points for N or M, which is a big departure, from the optimal assignment problems where N, the cost was cubic in N, so then typically anything above 2,000, for instance, was already a pain to handle. Now, for the more interesting part, I took care in trying to distinguish two areas in optimal transport, which is discrete solvers, on samples, and the more continuous flavor, of trying to extend those mappings out of sample. Let me try to provide a cleaner rationale for trying to do this for continuous distributions. So you can imagine that this continuous setting is essentially the extension in the limit of the permutation problem. So I have n points, and I'm going to n goes to infinity, and eventually, I start seeing densities. To the extent I have so many points that I start seeing densities. So I have two densities, and now the goal is no longer to assign one point xi to yj. It is simply going to be that of defining a map T that takes one point x in the support of my input measure and outputs a point T of x in the support of the second measure. And now notice I am using this push forward notation. So what does this push forward notation mean? It's really the same thing as permutations, but generalized with masses. It's essentially the notion that if I have a map T that is acting on every point in the support of the red measure, I will recover as the resulting measure, the blue measure. And so this is a constraint. I will be looking at push forward maps such that T sharp mu is equal to nu. And now I will be looking at the map that sends intuitively this red measure to the blue measure. Among all possible maps that send red measure to blue measure, what is the best map in the sense that if I collect the costs of all the x to T of x, integrated it on the first measure, then this is minimum. So maybe I'd like to insist a bit more on this. The push forward map here is a big thing to ask. And if you think about normalizing flow models or GANs or things like that, this is essentially what they're targeting. They're saying, I want to go from some distribution. So this could be, let's say, a Gaussian. And if I apply my sequence of normalizing flows, which is this map, I will get to the second measure. And so typically the way people would actually try to get closer to this equality is by throwing some KL divergence. This was discussed yesterday morning. KL divergence between this map, this result, and let's say the target distribution. So in optimal transport, this equality is just a start. So we're just saying, okay, among all of those great maps that can do the job, try to find that which is the most thrifty, in a way, that moves the less the points. And so although it might look like asking this is asking too much, we will see that if you use mathematics, and this is the second part of the lecture, and you actually dig a bit deeper into this, there are ways to turn this minimization into a very interesting and very useful inductive bias. So let me try to give a very short flavor, of what's to come on that area of continuous maps. Yes?
Question, is there any rationale behind calling T push forward in this case? Because it's basically just mapping.
So if you just remove this thing here, remove the equals nu, people will call this the push forward of a measure mu under the action of T. So you just give me any density. I apply T on all of the points of that density. I will get a change of variable formula if you want, and I get a new measure, which is somewhere else. And the fact that I'm asking that is equal to a target measure, this is where the constraint lies. So the push forward, of mu under T must be equal to nu. So this means that I'm not looking at all T functions, of course. I'm only focusing on, this family of T functions that do the job. And among all of them, I will try to find the one that minimizes this cost. And maybe I've glossed a bit about this, over this, but sometimes such a function T does not exist. So this is already a big, actually it's a big assumption to write, this mean, because sometimes you will see that they don't exist, and so there's a very simple example. Imagine, for instance, that I have my first measure, which is this. It's a Dirac mass, okay, at delta x. So this is my measure mu, and I have a measure nu, which is it's just two masses. So this is basically y1, y2. This is x. If you apply a push forward T to delta x, okay, so if I do T sharp delta x, okay, so again, if you think about this drawing here, I was saying, okay, I have a map T that goes from RD to RD that I apply to any point. If I apply T as a push forward to delta x, then do you agree that this is equal to delta of Tx? I'm just creating a new, delta mass, let's say, which corresponds at delta of Tx. So no matter how hard I try, if I am applying T to a Dirac mass, I can only recover a Dirac mass. And so there's no way I will recover, two Dirac masses. So even in that case, the problem is ill-posed. And so this doesn't even make sense. So it's going to make sense when you have well-defined, distributions basically which are absolutely continuous with respect to Lebesgue measure. You can relax a bit this constraint, but essentially you want to have mass that is well distributed for this to work. But if you, I think.
Sorry to interrupt, but
yeah.
In Caturovic version of the problem, or even in the synchronous regularized, we can do that, right?
Yes, of course. Okay. Of course, you can do that. I completely agree. So it depends a bit what you're asking. The synchron or Caturovic is a bit messy because it returns this matrix. A matrix is heavy to store sometimes. So sometimes you want to have a map, but the map is maybe not always well defined. But anyway, in the end, we will always use samples. So we will always, do some kind of source that will still be able to produce a map that works kind of works. So that's but indeed there's a bit two regimes, yes?
Just so I understand clearly, that counterexample does not work because the Dirac mass has mass 1, but if it was some mass A, you could still split it, right?
No, you cannot, because, I mean, even if you have, let's say, a mass, okay, let me do it differently. Imagine I have 2 points. Okay, sorry. Imagine this is, let's say, 3 masses. Okay, so I'm going to call it Y3. So there's going to be 3 here. And this is, sorry, probably some of you won't see this, but it's easy to guess that this is delta Y3. And imagine that I have 2 masses, like this. And so my mu now is 1/2 of delta x1 plus delta x2. If I push forward, those 2 half masses, I will get 2 half masses somewhere else. And this cannot coincide with those 3 1/3 masses. I cannot recover this distribution by just applying a function on each of the points and moving them around. Do you think?
Yeah, I think I get it, but I'm trying to map this to the discrete case where you had like an A1 delta x1, A2 delta x2.
Yes, exactly. So this is what happens when you are actually using the discrete case, and this is discrete already. Basically, down the line, here I'm basically saying that I cannot find a permutation that sends this to this. This is a bit like the limit, if I have 2 points and 3 points, I cannot have a permutation that says you are sent entirely here. And you are sent entirely here. Here I need to, as we were doing before, split a bit of mass like this. So this is going to be, let's say, 1/6, 1/3, 1/6, 1/3, and this works. But I have to split. And the fact that you are writing this split cannot be handled with this model where I'm just associating a point and whatever mass it is holding entirely to another point to bring all of the mass.
Okay, I get it. Thank you.
Yeah, welcome. So this is a lot more challenging as a problem. And the fact is that the first person that we can trace back this entire theory to is Gaspard Monge. And he wrote some memoir in the late 18th century. And the fact is that we had to wait basically for 2 centuries to see some results starting to pop up. So one of them was this Brognier theorem, and the other are results by the regularity of optimal transport. So recently, I don't know if you followed, but Luis Caffarelli got the Abel Prize about a month ago for his work in part on this problem. And so what these 2 and many more mathematicians came up with is a series of results that are really fascinating, in my opinion, and I will prove them later. The first one is this Brognier theorem that tells you that if the cost to compare 2 points is a squared Euclidean distance, so if here C is just x minus t of x squared in the vector space, then those optimal transport maps T, they must be gradients of a convex function. So let's try to parse this. So a convex function, of course, if I am in Rp, let's say, is a function that takes a vector and that outputs a number. Okay, and we all remember convexity, f of x plus y divided by 2 smaller than the average of f of x plus f of y. So, of f of x and f of y, sorry. And so if f is convex, and it's going from Rp to R, then necessarily its gradient is a function that goes from Rp to Rp, right? A gradient function of a potential is just something that associates a vector to a vector. And so what Brognier proved is that among all of those maps T that can do the job, there's only going to be gradients of convex functions that do the job correctly, that do it the best, and that actually have a minimal cost. So this means that you can forget about weird maps T's that are not necessarily, let's say, gradients of potentials, and you can forget about gradients of potentials are not convex. So you should focus on gradients of convex functions. And this actually opened up a lot of links between optimal transport and PDEs, but also schemes basically to solve PDEs in lower dimensions. And so there's two approaches that actually help to solve this problem then, taking advantage of this result. And there's one that is very famous that is called Benamou-Brognier, so by the same Brognier and a co-author, which will help you, compute this kind of arrows in dimension 2 or 3 by solving a PDE. And there's another link with the so-called family of Monge-Ampère equations. And this is more the work of Caffarelli and Figali, where again we are trying to characterize the solutions of this Monge-Ampère equations. So we're not going to do any PDEs in the course, so don't worry if you're not familiar with this area. But it's just to say that this insight yielded first tools, to solve this daunting problem of computing transport between two continuous distributions. So one exciting development that has happened in recent years is to start thinking about parameterizing optimal transport potentials, F, or optimal transport maps as neural networks. So as you can expect in machine learning, we have this hammer. We try to apply it pretty much anywhere. And so here what was interesting is that they actually considered neural networks that have a very specific architecture that I will go back to, which is this so-called input convex neural networks. So it's a neural network that takes a vector in and outputs a number, and the number needs to be convex with respect to the inputs, to the x. And so what they showed using standard duality is that this f star here, you can compute it as the solution of this problem by duality. I will go back to this, but this problem basically says the f here that gives you my best t star has got to be a function that is convex and which minimizes its integral with respect to mu plus the integral of its convex conjugate, f star, with respect to nu. So this is not an easy optimization problem, but people have tried it. And so this is left to a few those are the seminal works, and we're still seeing a lot of papers appearing recently in machine learning conferences trying to take advantage of this. Another problem that I would like to highlight, because I think it's one that pops up very often, is that of keep the story about matching. Remember the story about matching, and yes, please, you have a question.
Yeah. Is the convexity symmetrical between input and output?
So convexity is just going to be basically about taking a vector in, RP, and outputting a number. So I'm not sure what you mean by convexity here, but maybe you can help me.
I mean, like in the neural network approximation.
Yes.
Yeah, you were saying that the IC stands for input convex neural network.
Yes.
So could you elaborate a little bit more?
Yeah, I will explain this a bit more, but it's basically going to be a neural network. So so you have, let's say, your x. Okay, this is your input vector. So this is the same x that's here. Okay, and you're going to make it go through, a neural network that will have several layers, and in the end, you will just have one number. Okay, so I'm going to write this f that says theta, f theta of x belongs to R. Okay, and the only thing that I'm asking is that this function f theta of x be convex with respect to x, not with respect to theta, not with respect to the parameters. The thetas are basically all of the layers, the weights, and whatever. And there is a way to construct such neural networks that will be convex with respect to the input, and this is why it's called input convex neural network.
Okay, thank you.
I will detail this a bit later. Thank you. Another question.
Yeah, I have a question to the Bernoulli theorem.
Yes.
So it says if you have used the L2 norm, right, you get an optimal transport, so the function is convex.
Yes.
So what happens if you use a different norm, let's say like a different power? Can you still find an optimal transport?
It's a very nice question, and I will prove to you what happens when you have a different norm.
Okay.
So it's not going to be necessarily as easy as saying it is a convex function, but it's something called C-concave, a C-concave potential. And you will see the math is actually very fancy, but I mean, actually productive in the sense that you get nice formulas.
Okay.
Fascinating formulas. So there is another use case for transport that is associated with transport list is, okay, we're still going to be playing this matching game. You know, I have 2 point clouds and I want to find a good matching between the 2 point clouds, except I'm going to throw in an additional difficulty here, which is I am going to assume that the point clouds live in different spaces. So it's no longer easy if you want to compute the cost between the x's and the y's. So it's a bit as if you were looking at, you know, you want to assign a worker and a task, but you don't have an easy way to score the cost of, you know, assigning a worker to a certain task. But it's very easy to compare the workers between themselves, and it's easy to compare the tasks between themselves. And so although it sounds a lot harder to do this, and it's not easy to come up with an idea, actually, a lot of people have thought about this, and this is called the quadratic assignment problem. And here is a reasonable, I would say, solution. The solution is to say, okay, I'm still in the business of matching points. So let me try to, for instance, say that I'm matching x1 to y3 and x2 to y1. Okay, so this is a part of the matching. I'm looking at this. And does it sound reasonable to you as a matching? Well, intuitively it does a bit, because probably, you know, in your intuition, you've already figured out that a nice thing about this matching, although you know the points live in different spaces, is that it seems to be preserving a notion of metric, in the sense that here x1 was close to x2. I matched x1 to y3 and x2 to y1, and great thing is that y1 also seems to be close to y3. And so in a sense, my matching is isometric. And so this is quantified. How badly not isometric this matching is quantified by this formula. So why do we call this a quadratic assignment? Well, think about this. We're basically summing twice over p. And so here is the interpretation of this objective. If my p assignment matrix or transportation matrix, you've probably figured out by now that it's the same thing, to think about transportation matrices as relaxed matchings. If my p is assigning I to j, so if the mass between I and j is big, and the mass between I prime and g prime is big at the same time, okay, so I'm simultaneously sending this to this and this to this, I expect that the difference between the costs from xi to xi prime and yj to yj prime is not too large. So this is just what the objective says is, if I'm both matching I to j and I prime to g prime, then I want this square to be small. Because of course I will be minimizing this energy. So this is called again the quadratic because it's a quadratic function of p, and it's very intuitive. The bad news is that this quadratic function is not positive definite in this space of matrices p. And so this is an NP-hard problem. It's a very difficult problem. But you know, the modeling behind it is so interesting that people have worked a lot on this, and in particular, yes?
Can I have a question?
Yes.
Do I understand it correctly that in the mathematical sense it will be like the pushing forward the x's into some submanifold of y's or something like that,
yes,
with the additional constraint, yeah?
Of being isometric.
Okay.
Yeah, well, here to be fair, I did not really, I'm not introducing the continuous case immediately. So we're juggling a bit between, you know, this model of map and directly encoding a map discretely in a matrix. Here I'm choosing to do this in a matrix because it's well posed. Whether this can be translated to a map formulation and there's always existence of a map is actually a subject of ongoing research. So there's been a few papers recently on trying to find a T, a map that goes from, let's say, RP to RD, to different dimensions, etc., to find whether the existence of a map in that case.
Okay, cool. Many thanks.
Thank you. So, what can we do? Yes, please.
Oh. Okay, so I might be wrong here, but isn't this dependent on the first matching?
The first matching.
So let's say the first matching is X3 to Y3.
Yeah, of course. Here in this case, I just gave you what happened for one example that I chose.
Right. And when we calculate everything and then minimize over it.
How I am going to get to this minimum is not by doing this.
Okay.
Just like in the first optimal matching problem. If you do the first matching problem by just starting, this is my first, I decided to match this one, and then like a greedy algorithm.
So you can't do it.
You're not guaranteed to converge to an optimal solution. So nothing that I've been talking about recently uses a greedy approach. It's all going to be like optimization approach.
Thank you.
Yeah, okay. I think there was another question. Maybe not. No, it's okay. Okay. So how do we solve this kind of problems which are minimize an energy with a constraint? Well, there is a very simple approach to do this, and it's called, several people have different names for this, but conditional gradient or Frank-Wolf. The idea is to linearize this energy, so come up with a linear approximation of this energy, and solve the linear problem with those constraints. And so this was proposed by Facundo Memoli or let's say highlighted by Facundo Memoli about 15 years ago, who also formalized this framework and gave it this name of Gromov-Wasserstein distance between metric spaces, measure metric spaces. How does it work? Well, it goes as follows. It says, well, I am going to turn this into a linear objective by linearizing it. So I'm going to compute the gradient of this energy at my current estimate PT. And I'm going to try to improve on this by solving a linear program or a linear optimal transport problem using this P. So if you want the simple idea, the way you can look at this algorithmically is I have an energy of P, which is this. P is involved twice. I am going to act as if one of those two P's was frozen, and I'm going to optimize this one. And so this is really like computing this iterative process where I linearize and then I compute and linearize and compute. So it's a bit like there's so many names for this, like EM algorithm, etc. So you're basically freezing one part of the objective and trying to improve the other one, and then you refresh again and again. So you have PT plus 1, which is the minimum of this linear program. Let me say that if you introduce entropy here, of course, you help in solving this linear program, solving it using the sinkhorn. And again, we can also use the rank trick, the low rank trick that I was discussing earlier. And this, we showed this 2 years ago with Meyer. And this yields a linear time solver for Gromov-Wasserstein. And I will go a bit deeper into the details later on. Now, let me introduce you to the last beast in the zoo of optimal transport related problems. And this one is actually playing an important role for graphs, for studying graphs. So there's lots of work by various groups that are using this to use it for, let's say, graph matching. So the setup that we will be looking at is the same. We have two sets of points in two different spaces. So still we are not able to compare directly this location with this location. But now assume I give you some features per point. So maybe the more practical way to look at this is imagine those are nodes, and you also have a graph, let's say, that gives you some relationship between the nodes. But the nodes are attributed. They have feature vectors. And maybe the feature vectors are fairly long feature vectors. And so to each node, the node has a meaning within the graph, but it also has some information that is comparable across the two graphs. In that case, you can start with the first, Gromov-Wasserstein formulation, this quadratic formulation. So for instance, this might be the shortest distance on the graph or any other thing that you want to come up with that can compare two nodes on the graph. And you can throw in a linear term that will only depend on the features, because now it's easy to compare two features of those attributed nodes because you can just compute a cost function between two vectors, and here they live in the same space. So this is called the fused Gromov-Wasserstein problem, and if you look at this, it's very clear that this looks a lot like the previous problem. You have this quadratic term, you have this energy, you compute the gradient of that energy with respect to P. You have this term here, plus alpha times the matrix C3, and you can actually also use low-rank factorization to solve this. So maybe the intro was a bit longer than I expected. It's not a problem. I would like to highlight that all of those methods that I just described, including the continuous ones, are implemented in a toolbox that we called Optimal Transport Tools, OTT-JAX. So OTT-JAX builds upon JAX. I know that JAX was discussed a bit yesterday. So JAX is, of course, the framework of choice used at Google and at DeepMind. Yes, you wanted to ask?
Yeah, no.
Yeah, I personally like it a lot. I like it a lot because I think it's the very natural framework for mathematicians, to do automatic differentiation. And maybe one simple way of highlighting it. I know that PyTorch has some functional modules now, but they are not. JAX is entirely functional from the bottom up. And so what I like about it is that it's really functional transforms. Everything in JAX is about functional transforms. So if you think about PyTorch, typically you would call the gradient on an evaluation of your graph. So this looks a bit like coding grad on f of x. Whereas in JAX, really everything will be creating a function that is the grad of f and applying it on x. So why is this useful? Because then you can call, let's say, the Jacobian of the grad, which is the Hessian. You can do, you can compose, if you want, different derivatives very easily and very naturally, and even check, things numerically. It's very intuitive. Whereas this I think is more like a bit of a mathematical aberration. So this is what we're taught in high school not to do. Don't put fx prime, but write f prime of x. And so this is one of the things that JAX is good at. Arguably, it's not as well documented and not as widespread as PyTorch, but I think it's actually gaining steam. So if you like maths, I think this is one of the strong assets of JAX. And our JAX is a toolbox that we've been developing with colleagues at Apple, and we've also received support by people from Meta and Google. And one of the things that OT will do is implement all of the algorithms that are presented, and in most of the cases, provide like a citizen first, like an end-to-end differentiable pipeline, in the sense that the computations that we do can be back-propagated easily through in learning pipelines, and I will explain a bit later why this is important. So yeah.
So I might be missing something, but yes. Why didn't you try to map the points in the two spaces to one common space? Like
yes, of course.
Kind of embedding, or
well, imagine, of course, if you want to do that, what you need is to have matched data. This is a very good question. So, okay, imagine I have pairs of images and text and labels. Okay, so a cat running in the beach, a picture of the cat running in the beach. And then let's try to map those two instances in the common space, and with the supervised information or label information that I want the embeddings to look somewhat alike. Here, by design, I'm placing myself in the scenario where I do not have this labeled pairs. So here, okay, it's a bit maybe I should have on purpose added different numbers of points. But here my goal is really to match two different sets of points, maybe 5 and there's 8, in the other set, and I don't have supervision. I don't have matching.
So this doesn't work with like, I don't know, some unsupervised algorithm which maybe find some cluster of common features.
Okay, so imagine you run 2 VAs on this data set and this data set. How do you ensure, because the VAs will have a lot of invariances, and you will be able to have every rotation basically of your points in the VA will typically yield something is comparable. There is a symmetric problem that you cannot disentangle basically. And so it won't be possible to find a common embedding space that is meaningful in that sense. Okay. So this is a very good question. This kind of problems are when we don't have labels of matched points. I would say that this is also the case more generally from the beginning, in the optimal matching problem. If, for instance, you give me the blue and the yellows, and I was able to see that this one is this one, and this one is this one, then this becomes a regression problem. And I will try to find, let's say, a map such that T of xi is not too far from yi. If I have pairs of xi and yi labeled, as pairs. But all of this is basically when I don't have access to that information.
Okay, thank you very much.
So this point is very relevant because there are some settings where you could be in somewhat a semi-supervised setting, where part of the labels are known, part of the matches are known, and a lot of the matches are not known. And so in that sense, you can try to leverage the partial matches. This is also a topic of ongoing research. Yes?
So you said that this could be also solved for the problem that one of the spaces has more points than the other one.
Yes. So essentially, if you look at this, I wrote everything in terms of P. So it's basically a transportation matrix. So I can split, 1 point. They need to be of the same total mass. That's the only aspect.
So could it help, for example, if we have two sets of equations, so we have two sets of space, and we want one of them should be the simpler version of the other one.
Yes.
So we want to optimize and see which parameter we should optimize to get the most similar features from the other one.
Yes.
We can do.
Yeah. So this is why it's interesting what you're saying here. Here, indeed, I described an object which is some kind of energy, and you're asking, can I optimize that energy in a way with respect to some parameters? So maybe I want to move some of those points. Maybe I want to change some of those features. And the answer is yes. But then you need to be able to differentiate through this. And it's actually possible. I'm happy to go into the details, but this should be easy to do.
Thank you.
And this also why programming all of this in odd JAX or within a JAX framework helps, because all of the gradients of the energy we want to get them for free, basically. So
sorry, is
yes?
JAX faster than PyTorch, for instance, for optimal?
Oh, you have a lot of benchmarks that will show speedups, relative speedups. I mean, it's a competition out there, right? Okay. So one day one it will be faster than the other. So JAX builds on XLA, which is this compiler. So most of the speedups of JAX rely on XLA speedups. So typically XLA is good, but maybe not as fast as custom-made, CUDA kernels. When you run on GPU, XLA would be very fast on TPU. On CPU, maybe it doesn't make such a big difference. So overall, I would say JAX is competitive with PyTorch. That's the big difference, I would say, another conceptual big difference between JAX and PyTorch is that JAX is not a neural network library. JAX is really NumPy on steroids, where you are basically giving it a bit like Numba, but you can compile on other platforms, other accelerators, plus automatic differentiation. Then, if you want to use neural networks with JAX, you need to use other libraries. So there's a few famous ones, but maybe one that stands out is Flax, and so the entire ecosystem of JAX, starts to look a bit like PyTorch, because PyTorch does a bit of everything. But I think it's a very clear, guideline of the JAX, of people who maintain JAX, that they don't want JAX to be a neural network library. They really want it to be just simply lower level in the stack.
Makes sense. Makes sense. Maybe a second technical question, because we mentioned earlier this. What is the trade-off between this dimensionality with the low rank?
In the low rank approaches?
Yeah.
I will go a bit more in details later.
Okay, sorry.
When I explain the method.
And I think one more question.
Yeah.
I don't know if you're going to go through this afterwards, but is there perhaps an intuition on why the optimal maps are Hessians of convex functions? Like,
so they're gradients.
But is there like an intuitive explanation of why is this?
No. honestly, I would love to be able to give you an intuition, but for me, the proof is very clear, but I don't have a very clear geometric intuition.
Okay.
I mean, you can visualize, that if you follow the gradients of convex function, you're doing things kind of in a neat way, but I don't have much more than that. Yes?
Thank you for the great introduction. I was just wondering, is the optimal transport map unique? Or can you find different maps that have the same cost?
So in the convex case, in the Brognier theorem, I think it's unique. If you really want to have uniqueness, I mean, there's going to be a few technical, I would say, assumptions. But let me think about it. On the top of the head, there are cases, of course, where it's not going to be unique.
Okay.
Like, so in the Brognier case, the densities make things very smooth, etc. But imagine, okay, you remember this example? In that example, things were not working well. Here, I'm going to make an example where things work well, and they work so well that we have actually two maps. So imagine you are, maybe, you have a square, okay, and the two red points are here, and the two blue points are here, okay, and I'm going from red to blue. It should be quite clear that I can either go like this, or I can go, I don't know, like this. Okay, so here the Morse problem is well defined. Although, well, typically the Morse problem will be well defined on discrete data if you have point clouds of the same size and same weight.
Okay. So basically, if you want to go from this position A to C, yes, passing through B, for example, yes, you cannot find an optimal transport map from A to B, and then from B to C, and just compose them?
No, that's not true.
Okay.
No, typically you cannot compose optimal maps.
Okay.
I mean, even if you think about it, this is a far-reaching, I mean, I think interesting observation. Imagine I go from mu to nu, and from nu to rho, okay, to the distributions. In principle, if I use the squared Euclidean distance as a cost, okay, then let's say my T star from mu to nu must be equal to some gradient of a convex potential. Let's call it F mu nu, okay? So this is F mu nu is convex, okay? And T star nu to rho, again, as you can see what I'm writing, is going to be, or maybe let's make it a bit clearer. And let's write this one F and the second one G. Okay, so it's easier. G is convex. If I want to go from mu to rho, sorry, of course it sounds like taking grad of G applied on grad on F. Sounds like a reasonable way to do this, right? I'm starting from mu, grad F applied to mu gives me nu, and then applied to grad G applies to this gives me rho. But this, in general, is not the gradient of anything, and not even a gradient of a convex function. There is no h such that grad h is equal to this. It doesn't, I mean, there's tons of counterexamples, and not even the potential, basically. Okay. So without even mentioning convexity. So it's not going to be, so maps are nasty in that sense. The composition of maps, of course, gives you a feasible point, but not an optimal one.
Okay, thank you.
Can I have a question?
Yes.
Okay. I was wondering if all these approaches works well, also if you are working in high-dimensional points like neural networks, latent spaces, or if you have to face some known problems.
Yeah, this is a very, very good point. I introduced mostly those hacks, you know, or computational modifications from the linear program, mostly for a computational perspective. And I told you it's either cubic or these things. It turns out that indeed it's not only good from a computational perspective, it's also better to do those kind of, you know, regularizations from a statistical perspective, because you do pay the price of dimension. If you want to estimate transport or transport quantities such as Wasserstein distance, it's well known that if you focus on samples, you're extracting too much juice, if you want, of the samples, you're overfitting, and as a result, the quantities you get really are bad estimators of the true, let's say, Wasserstein distance between the two densities. So those regularizations are actually also acting on the statistical sense.
Okay, thank you.
Okay, so so today I will have to speed up a bit, but I will introduce two things, which are those entropy and synchrone algorithms, entropy regularized and synchrone algorithm. This is essentially to provide a solid foundation for the estimation of those quantities on samples. And then I will move towards the Brognier theorem and neural network implementations. So again, let's cover a bit of ground. But I still have a bit more time because we started late. Okay, good. I have a bit of a slack. Okay, so we have two probability distributions. Again, we are in some space. We have some costs. And here we are going to parameterize optimal transport. I didn't talk too much about this, but the very natural intuition, and I want this, you know, to be in your heads, is that we have, again, when you have discrete samples, to keep in mind that this is a model for the distribution of scarce resources. So typically one possible analogy is to think about factories and mines that get some resource and send it to factories. There's a lot of other analogies. I think in Cédric Villani's book, he basically mentions baguettes made by bakeries sent to restaurants. Another analogy is like the troops, you know, moving troops around, etc. So imagine you have factories, and again, the size of the Diracs is basically how much amount of resources produced, and the location is basically where this factory is. So the conservation of mass principle, as I explained, is basically that the mines must capture the resources, and each of the N mines must send all of its production, and each of the M factories need to get the resources it needs. And so what we will try to do is come up with this model for an optimal transport. And I've insisted on this, but let me just explain this the last time. This is going to be a problem defined on matrices in this Kantorovich setting. So we will have 7 times 6 matrices. And if you think about from here how you actually come up to a matrix problem, well, first you number the locations, and then you add the masses, row sums, column sums, and this is going to be your unknown. This is going to be your variable. On the other hand, you will get that the geometry of the problem is going to give you the other matrix. So it's going to be, on the one hand, unknown matrix that satisfy the row sum and column sum constraints, and a known matrix which is given to you by the geometry of the problem. So here is where the cost is injected, which basically tells you what is the distance between each of the red points to each of the blue points. So here, for instance, if I look at, if I look at this, it didn't really show here the shade, but if I look at this point, this entry here corresponds to the distance between the 5th red mass to the 2nd blue mass. Now, the linear program that we will try to solve, again, is this minimization over P in all this set of matrices against the cost of P against this. So as I mentioned earlier, this is a linear program. And if you know a bit about linear programs or more generally optimization, what you know is that to every linear program, or to every convex problem, or even to every optimization problem, there exists a dual. So what is the dual of this optimal transport problem? So maybe a good thing to remember whenever you think about duality is, on the one hand, you see that there are two blocks, in this optimization problem. You have the constraints of P and the definition of P as a variable, and the objective here, okay? And so the idea of duality is somewhat to reinject what constitutes the constraints up as an objective, and to reinject whatever was in the objective here as a constraint. And it's going to be done in the following way. If you count the size of the variable of this problem, it's n times m, okay? On the other hand, there are n plus m constraints here. So in duality, the size of the variable, in the constraint here will stay here the same as the size of the constraints in the dual problem, but the size of the variables in the dual problem will be equal to the size of the constraints in the first problem. So, in other words, the dual problem to this linear program involves two vectors of size n and m, and the reason I'm color coding them in red and blue is because there is as many values alphas as there are weights A, and as many betas as there are Bs. So in the dual problem, the size of the variables is n plus m. There are nm constraints here, whereas here there were n plus m constraints. And the nm constraints are actually derived from the parameter that was playing a role in the objective here in the primal. And those n plus m variables interact with A and B here, which were in the constraint. So if you want to, you flip over, the data, where the data that was appearing in the objective comes into the constraints, and the data that was appearing in the constraint appears now in the objective. So I'm sorry, this is a very short, very, very cryptic introduction to duality if you've never seen it before. But one of the reasons why Kantorovich got a Nobel Prize in the 70s is arguably because it was one of the first ones to formalize duality in linear programs in the 40s. So the solution to this problem is the same. The quantity here, I call this WC, like Wasserstein with this cost C. There's a bit of a abuse of notation, because depending on C, this may not, with Wasserstein may or may not be a distance. But let's keep it this way. So what Kantorovich showed is that this problem has the same value as this problem. Now, let's think about implementing those two linear programs on one example. So suppose I have my mines, the red mines, and I have the blue factories that are in the map in R2. And suppose I am using the square Euclidean distance, as a distance between points. So suppose I run, the optimal transport solver. So I'm going to run the primal problem. What I get is typically a solution that would say, okay, you send some of your mass here, here, here. This one sends the mass there. This one sends the mass there. This one sends the mass there, etc., etc. So this is, I think, what we all have an intuition for, when we talk about optimal transport. Here is the solution of the dual problem. So what I did here is just simply run a solver, get two vectors alpha and betas. alpha I plus beta j is smaller than this, and then I have this. I have to maximize this quantity here. And what I just did is plot using color coding in every point xi and yj the value that I get in those vectors. So here what you can see is that all of the values for the red squares are very negative, and all of the values for the blue circles are quite positive. So the way you can interpret duality in this case is as follows. Imagine I am a company, and again I'm running the factories and the mines, and I want to look for an optimal transport between those mines and the factories. So I will have to solve my cubic problem. It's complicated. I don't have time for this. Instead, what I will do is I will ask some delivery company, I don't know, the Poland Post service, to do this. And here is what I'm going to ask the post service, or the post service. Here's what the post service proposes. It says, I am going to charge you an amount alpha I of money for every kilo of the resource that I need to pick at point xi. So this is going to be my, if you want, pickup cost. And I'm going to charge you an amount beta j to deliver at the factory yj. So the postal service has a very simple pricing system. It just says, I charge you to pick up stuff somewhere in one of your factories, one of your mines, and I charge it to deliver it in one of your factories. And I'm going to give you a very simple pricing. It's going to be only dependent on where you want me to pick up and where you want me to deliver, and just let me handle the rest. So if you're the postal service and you want to provide an offer basically to the company, you're going to try to maximize your profit. So what is the profit that you're making? Well, every time I'm picking some mass at a point xi, and the mass is going to be, let's say, ai, I'm going to multiply it by the price per unit of good that I'm charging. So it's going to be the dot product of alpha I times ai. And I'm also charging to deliver, beta j times bj. So this is basically what the total scheme will give me as the postal service. On the other hand, what this company knows is that there is a cost, there's an established cost if you want to go from one point xi to another point yj. This is, let's say, the market price for delivering goods from xi to yj, for delivering 1 kilo of goods from xi to yj. And so I want to maximize my profit. I want to make it as big as possible. But if I come up with a price alpha I to pick up a good at factory xi, and a price beta j to deliver the same good at factory yj, if that price is bigger than the established cost of the market, then it's going to be easy for the company here to figure out that I'm basically taking advantage of the company. So in other words, you can interpret those alpha i's and beta j's as prices, marginal prices, for moving the mass around optimally. And let me try to give you a bit of an insight here, because I think it's going to play an important role later. There was a question asked earlier on trying to minimize a notion of distance, Wasserstein distance between 2-point clouds. Imagine again, you're running this, and these are the resources, the minings, and these are the factories. Imagine that I have the freedom to move factories. Okay, maybe in my 10-year plan, I have the ability to move those blue points. What would be, at least locally, a reasonable way to move those factories? If I look at the map, it seems like moving this one in this direction might do a great job, right? Because this one in this configuration seems to be served mostly by this one, which is very far from it. And so it seems like moving it in this direction might make, might help a bit. Of course, if I move it too much, maybe this optimal transport is going to change. So I'm not sure exactly what's going on if I make too big a step. But at least locally, and this is the idea of a gradient, it might make sense to move this one in this direction. Equally, it might make sense to move this one in somewhat an average of those three, etc., etc. So this is, if you want, the location perspective. Now imagine it's not about moving the factories or the mines that I will be trying to act upon, but I will try to act upon quantities. Okay, no, moving factories is a mess. It's too complicated because the factories are already there. But what I can do is maybe ask this factory here to decrease its production and this one to increase its production because it seems to be better positioned, or even better. Maybe I want to decrease this position and increase the production of this factory here because it's very close to the mines. Where can I get that information? I will get that information in those prices, essentially. Because what those prices tell me is that it's a lot more costly to pick up, to deliver goods at this factory than it is to deliver it at this factory. So you might see some of the prices are negative, but this is not a contradiction. If I'm, the post, I can tell you, okay, I have to pay you $10 to pick up here, but you pay me $13 to deliver there. So it's minus 10 plus 13. I still get money out of this. So it's not a problem to have negative prices if in the end this is positive, right? But this is what you can then see. You can have some notion of relative prices. What really matters is the relative price of this one, which is 20 to deliver here, whereas it's already 45 or 50 to deliver there. So if I want to just in one look figure out where I should increase my production, it's probably here, and decrease it here or here. Okay, so this is the dual perspective, and it also provides you this notion of differentiability. So now let me go to the geometric interpretation of all this. Anyone that has done a linear programming course, I'm sure, has seen this kind of picture. The set of coupling matrices that has the marginals A and B's is basically this polytope. It's a set of matrices, non-negative A and B as row sums and column sums. So here we are in a space of matrices, and this MXY, remember my other matrix, it can be seen as some direction in this space of matrices. Okay, I can, if I want, I can unfold basically a matrix as a very long vector and get this kind of picture. Now, what I will be looking at, if you just follow the standard linear programming route, is that you want to find the vector in this point in this polytope that is the least aligned, if you want, has the smallest dot product with M of xy, right? This is the idea. I want to go minimize the dot product of any point in here with respect to xy, so I'm trying to go as much as possible in the opposite direction as mxy until I hit some corner. And actually this is what happens. You will almost always hit a corner of this polytope, and this is a P star, and so this is a beautiful linear programming theory of how to get to one of those corners. And if you've never studied the network simplex or the simplex algorithm, know simply that the simplex algorithm is an algorithm that moves around by jumping from one corner to the other until it finds this best optimal corner. The bad thing about the simplex algorithm is that it's very expensive. And there is another, I would say, a bit of a issue with the simplex algorithm, or linear programming in general, is that the solution P star, if you define this criterion with this linear criterion, is not always unique. But that's, to me, the fact that it's not unique is more hiding something a bit more fundamental, which is that it's a bit unstable with respect to the data. Let me try to give you an intuition for this. Suppose this is my setup, my factory is my mind. And now suppose I'm changing a little bit where the locations of the first mines are. I'm going to wiggle a little bit. For a while, nothing is going to happen. Until magically, sometimes, this has zero chance of happening, of course, in practice on continuous data, but I will be hitting a facet in the sense that this direction will be orthogonal to this thing. So this never really happens. But what happens is that the second I have gone slightly too far, I have jumped in a discontinuous sense from this vertex to this one. And if you think about, the entire picture of deep learning, let the gradients flow. I want, end-to-end differentiability. It's important to have some continuous and gradient that I can squeeze, to learn, etc. This is horrible because basically this says that, the solution was this for a while, so it was not moving at all. So if you want, the Jacobian of P star was not changing at all with respect to the inputs, and then all of a sudden, back you go to another point. So this is yet another issue, in the definition of linear programs. And I'm also going to give you I would say, programmatic reason why linear programs are bad is because they don't really run on GPUs. Sorry. So essentially, they're very, incremental, sequential algorithms that make a lot of sequence of steps. And this is the implementation, which is arguably, I think, one of the simplest that I know in C++. Of the Earth mover's distance, which was proposed in the late 90s. This is the same idea. And so the network simplex is a beautiful algorithm in mathematics, I would say, but it's actually very hard to parallelize and implement. So what we want to do is get something a bit more better behaved.
Sorry?
Yes?
Can we stop here but fortunately we have second parts, right? So
sure. Let me just stop after this slide.
Of course.
And that's great. So I told you that everything was hard. I just want, before we take the break, to highlight two cases where actually optimal transfer is a bit easier, and you might want to have this in mind. So there's one case where everything works very well and is very simple. It's the case where your country is a line. Okay, so if you're like a Chile, you have this long line and you have basically factories and you have mines and they're all more or less on a 1D curve. In that case, optimal transport is extremely easy to solve for reasonable costs. I can talk about the cost, but all of the costs that you can think about, the square Euclidean cost, the distance, etc. And how it works is the following. It just says whatever is to the left, you start transporting as much as you can, and then you fill basically progressively. So you have this greedy approach that was mentioned earlier. So for instance, this first mine is the first on the left that I see. It just sends whatever it has until it fills this demand. There's some left here, so whatever is left here goes here, and then you can see basically you can play this game where you fill up, all of the demand. And so you have this kind of, crossed assignments, but you can guarantee that this is optimal. I'm happy. I don't have the time to cover this today, but it's one of the cases where optimal transport is, as usual in 1D, things simplify a lot. And I don't have time to go into the details, but also for Gaussians, for continuous Gaussians, there are closed form formulas if you use the squared Euclidean cost. So those are the two easy cases. But apart from this, unfortunately, there's no easy formula. So see you in.
Do we have any questions, maybe, regarding the first part? Okay.
Hi. Yeah. So for continuous Gaussians, does the formula is same as the KL divergence?
No, it's completely different. No, it's completely. Actually, it's an interesting formula. I can direct you to the book or it's a linear. It's an affine map basically. Actually, not only can we compute optimal transport and like the distance, but we also have the Monge map in general, unless you have degenerate Gaussians. But it's an affine map. The Monge map is t of x is equal to ax plus b.
Okay.
So if you want, I can show you this on the board.
Okay. Thanks. Yeah.
Thanks for the nice intro. You mentioned that when you add a regularization term to the network simplex model,
yes.
The mappings are not as sparse. So
yes,
fail to see why that is the case. So if you can explain.
Yeah. So essentially, whenever you have a linear program has a certain amount of variables, a certain amount of constraints. So here it's nm variables. If I just go here, it's nm variables and n plus m constraints. No matter what the linear program, if you have nm variables and n plus m constraints, you will have a solution that has only up to n plus m non-zero values. So this means that you have a matrix of size nm, and it only has, let's say it's 100 times 100. It can only have 200 non-zero values. This is like a direct consequence of linear programs. Whenever you're going to throw some regularizer, you're no longer a linear program. You become a convex, linearly constrained convex problem. And so in most cases, you won't be that sparse, basically.
Okay, thanks.
Can we have multi-dimensional marginals for the dual thing, or?
Yeah, of course, there is a multi-marginal optimal transport problem. So you can generalize this from a matrix to a tensor if you're considering multiple distributions at the same time. And then you have to define a cost on like triplets of points or costs on quadruplets of points, etc.
Why do we not count the positivity as NM constraints?
So because in linear programs, there's various ways of writing them, but one of the standard what people call the standard form is non-negative variables is given, equality constraints, and some objective which is linear. And you can always come up with the standard formulation of a linear program. So the fact that you're adding them here or you're adding them as constraints, etc., is just the same thing. It's just in the end we have you can also have inequalities. There's various ways of having a linear program includes all of equality and inequalities, but you can always using slack variables and just reorganizing terms come back to something that looks a bit like this: non-negativity of all the variables plus linear constraints.
Okay, I believe more questions after the break, so we will see each other here 10 past, okay? Thank you.
Again, I just wanted to conclude on this. I mean, to take over from this last slide. In 1D, things are easy, and for Gaussians, things are easy. Let me just briefly mention that this basically yields two tools that people like to use. One is the sliced Wasserstein distance. So the idea of the sliced Wasserstein distance is to project high-dimensional point clouds into one-dimensional projection. You sample some direction and you project. And so if you have 2-point clouds, you just sample one direction, you project both on 1D, and you get this kind of picture, and then you can compute the Wasserstein distance in 1D, and then you can repeat this process repeatedly over multiple directions, and this yields a simple approach that is inspired by optimal transport, but is not really providing an optimal transport map or things like that. So this is called the sliced, and this is the Gaussian thing. You might have encountered this under the name of Fréchet inception distance. People have been using this closed form formula for Gaussians. But I don't really have the time to go into this. I will move back to this goal of trying to compute the Wasserstein distance for 2-point clouds. And if you summarize what I just told you so far, it looks like the Wasserstein distance as a tool is a bit doomed to fail. It doesn't look like a good tool. I don't think I should be able to convince you right now to use optimal transport and the Wasserstein distance in particular. Why? Well, the first thing that I told you is if you give me 2 samples from 2 measures, what would really matter to practitioners is if you give me n points and m points, and I know that those, because we are in a statistical learning setting, a machine learning setting, those samples come from some distribution, underlying distribution mu and nu. The first thing you should be worried about is I just told you that computing the Wasserstein distance or approximating it using samples is basically log cubic log n. Okay, so it's extremely expensive. The second thing that you might want to ask is, what sense does it make for me to compute the Wasserstein distance on samples, and does it look anything remotely like what would be the true distance between the true densities. So if you want, there is a computational aspect to this. So it's like the computational complexity. And there should always be, a statistical complexity element to whether you want to use this tool or not. And it's basically, how different is it, okay, you're telling me that the Wasserstein distance between two samples costs this to compute. Once I have it, do you have any guarantees, at least, that this is going to be looking a bit like this? And the answer is no, not at all. It's actually terrible as well. So terrible in what sense? Well, it's terrible in the sense that if, to simplify, we have two measures which are the same size, endpoints, and we are in a Euclidean space of dimension d, then essentially what you should expect is that the Wasserstein distance between the samples converges to the Wasserstein distance between the densities at a very, very slow speed. And the speed is basically n over 1 over n power 1 over d. So this is what people would call the curse of dimensionality. So if you just look at those two slides, those two boxes here, you should just simply leave this room and say, okay, I'm not interested in optimal transport. This is not useful. It's super expensive to compute. And also, it's very unstable from a statistical perspective. So this is why I want to emphasize that all of the things that we've been pushing, in OutJax and all of those toolboxes have clearly, those limitations in mind. The one thing is we want to have something that is faster to compute. And the other thing is we want to have something that is better statistically behaved. And so this was a question that was raised before. And how do we get, things that are better behaved statistically? Well, it's the same thing as saying that we want to avoid overfitting because we don't have enough samples. And so we have to regularize in a way or another, add some inductive bias, when we're estimating any of those quantities, whether it's optimal transport maps or just simply couplings, etc. And so we need to change the problem to get something that is better behaved. So I think it's a canonical example of the maths are beautiful. They consider that they have access to the densities, have access to a lot of information, but you should not translate those insights in math in data sciences, because in data sciences we always have, a different set of constraints. We have a limited amount of data, and so it doesn't really work. So one of the classic ways of regularizing the coupling problem, the optimal coupling problem, is this idea of the synchron algorithm or the entropic regularization. So just to be brief, the motivation is essentially, I just told you that getting here to this P star was costly, that it was going to overfit the data in the sense that this matching was going to be very brittle. And I show this that it was brittle in the sense that if you move a little bit, the input points, you would jump, around into different corners. So the goal here will be essentially to come up with a solution that is maybe not as good as P star, but that is going to be moving more smoothly with respect to the data, and that we will get to more quickly. And so one solution is to use this idea of entropic regularized OT. I mentioned it, in the first slides. It's just adding this entropic penalization. So let me just try to give you an intuition. Here we started from the linear program. I'm adding the entropy. The first thing I wanted to emphasize is that here entropy is just this sum, it's Pij log Pij minus 1. And why does this work? Well, one of the things is that those P's are all non-negative, and the Pij sum to 1. So it really makes sense as the entropy over probability distribution. Now, if I want to illustrate a bit the impact of entropy, let me try to take this example. Imagine I start with gamma equals 0. So I have this distribution in 1D, this distribution in 1D. So suppose this is discretized along 100 bins, discretized along 100 bins, and I'm going to compute the optimal transport map. So here the optimal transport variable is of size 100 times 100, 10,000 values. And remember, I mentioned this earlier, because this is a linear program and I'm in the regime where gamma is equal to 0, this matrix of size 10,000 can only have up to 200 non-zero values. So this is why it's actually very hard, to see the non-zero elements, because they're kind of, flooded by zeros everywhere. But you can actually see a bit the trace of those things. So basically, this is what this would look like. And what happens when you start increasing gamma is you're minimizing and you are subtracting entropy, so which means that you want more entropy. Okay, you're minimizing minus gamma entropy. So this means that if you look at this matrix, it's full of zeros, has a few non-zero elements which are barely visible, which means that it's clearly not a matrix with high entropy. It has extremely low entropy. It's almost a deterministic, matrix. Think about this as a probability distribution on the square. I'm basically telling you that all of the mass is carried on a very thin line, which is it's highly non-entropic, right? When I start throwing in some gamma, here is what the optimal solution would look like. So what does it mean here? It means that I'm starting to add a little bit of blur because I want something that is blurry, because I want entropy. What you have to take into account, though, is that if I were to take this image and start to put like a Gaussian blur everywhere, I would get something that is a bit blurrier, but something that will not satisfy the marginal constraints. The row sums of this would not be equal to the row, to this, and the column sums would not be equal to this. So essentially what I'm doing here is I'm asking more entropy, but please still keep the marginals. So what it's going to do is some kind of adaptive addition of blur in areas where I'm not worsening too much the cost. So what I have a trade-off between adding blur in areas where it's not changing too much the cost and still keeping the marginal constraints. And so you can see what happens when you start adding entropy and you start adding entropy. And so my question to you is, what happens when gamma goes to infinity? Yes? It's not complete blur, because remember, we need to satisfy the marginal constraints. So we still have a P which has row sum A and column sum B. So what is the coupling with the highest entropy that has marginal A and marginal B? No, this has very low entropy.
Okay. Yeah.
So the joint, it needs to be one, because there's many joint distributions. I mean, all of those are joint distributions that satisfy the couplings. The independent coupling. And the independent coupling is basically equal to, I don't have the red anymore. But so if you want P infinity, it's going to be equal to A times B transpose. This is the dumbest and simplest coupling you can think about. Sorry? Most of them? Yes. Yeah, so here, for instance, there's going to be, if this one, there should be 4 little peaks, basically. One big peak here, which corresponds to the two peaks, and then one, which is this peak times this one, a small peak here, barely visible, and then this one here. So what is nice about this coupling is I don't need anything about the data, about the cost matrix to come up with it, right? It's very easy to say that every time you give me one distribution and another, I can just compute the product coupling, or this what people call this independent coupling. So it's basically coupling 2 random variables by just assuming that they're completely independent. So the probability of having x and y is just equal to the probability of having x according to the first measure, and the probability of having y to the second measure. So this is just simply going to be the matrix A, I, B, J, I, J. And it's very easy to see that this matrix actually does satisfy those row sum and column sum constraints. Because if you sum over a line, you're just summing over the B's. If you sum over a column, it's just summing over the A's. and this is basically equal to 1. So what we will try to find is a trade-off between the two, okay, when we add this entropic regularization. Beyond this intuition, the important thing from a computational perspective is that it turns out that it's very easy to compute this P gamma. So the first thing to notice is that this is a strongly convex regularizer on the simplex, and therefore this is actually defined uniquely. So we really have one unique P gamma, whatever the problem that you give me. There's no corner that jumps around or a facet or things like that. And the fantastic thing about this regularization is that it will give you an explicit factorization of the solution. So remember, with a linear program, it was not very easy to figure out what it would look like, except that it was very sparse. Here it's going to be as follows. If this is the solution to this, then there must be two vectors which are non-negative, or actually positive. One is of size n, and one is of size m, such that this transportation, this P gamma, the optimal one, is equal to diagonal matrix of U times K times diagonal matrix of V. And this K matrix, actually, I know it. It's the exponential, element-wise exponential of the cost matrix divided by gamma. So how do we get there? I want to be a bit brief here, but it's just very simple first order, method of Lagrange multipliers, like the 0.1 method you see in constraint optimization. What does it do? It says, well, here there is an objective which depends on P. So it's sum of Pij times Mij plus gamma Pij log Pij minus 1. Okay, so you're summing. This is just the objective. And then there are two non-negative, two equality constraints. The two equality constraints are that P times 1 is equal to A and P transpose 1 is equal to B. And so what I am just going to do is introduce Lagrange multipliers for this. And here, notice one interesting thing is that because I'm using entropy, I don't even need to encode for the non-negativity of P. Because if I'm using a log somewhere, of course, naturally, if I have a log of something negative, this will blow up, and so this will spit out, an error. So we don't even need to take into account non-negativity constraints anymore. So the standard approach to handle this kind of constraint optimization problem is to objective plus Lagrange multiplier for each of the constraints. And then if you just do first order conditions, what we get by just reorganizing some terms is that the optimal solution should have this form. Every element Pij is exponential of some quantity related like Lagrange multiplier divided by gamma, exponential beta j divided by gamma, times this exponential minus Mij divided by gamma. So this is exactly, if you just rewrite this like this, Ui as this thing, Vj as this thing, it's basically this form, okay? So we know, just by using this approach, that the P matrix, the optimal one, has this nice factorized form. And here, the reason I'm writing this kernel, this matrix K as kernel, is that if this is a distance or a squared distance, typically this is going to look like a Gaussian kernel, pairwise Gaussian kernel matrix. So now the question becomes how to find this vector U and this vector V. And so this is the basis of the Sinkhorn algorithm. The Sinkhorn algorithm does the following. It says, I know this is the matrix that I'm looking for, and I just need to make sure that this matrix has the right column sum and row sums. So I need to find a U and a V such that this matrix has row sum A and column sum B. What does it mean? Well, if this matrix is in the set that I want, the sum of the rows of this matrix is equal to A. The sum of the columns of this matrix here is equal to B, which I'm just transposing basically this matrix like this. Now, this is two sets of equations, okay, N and M equations. Let's try to parse them a bit. So diagonal matrix times vector of 1 is just equal to the vector itself. I think this is pretty clear. If I have diagonal matrix times the vector of 1, I'm just multiplying each element by 1, and so that's it. So I can simplify this. Now what I get is that a diagonal matrix times A vector is equal to A, and the same thing here for B. This means that diagonal matrix times the vector is essentially the element-wise product of two vectors. Okay, so it's it's basically the ith element of this times the ith element of this all over, which I can rewrite simply as saying that U is equal to A divided, element-wise again, by KV, and V is equal to B divided by K transpose U. So here what I have is a set of two nonlinear equations that U and V must satisfy. So it's not trivial to solve because there are a few numerical issues that might arise. And typically, you know, if this is equal, one of the entries goes to 0, then this blows up. But apart from that, if I have this set of two nonlinear equations, a simple approach to solve it is to use a fixed point algorithm. So I want to find U and V that satisfies this. Well, the first thing I do is I make sure that U satisfies this. I update U, and then I update V, and all over and over and over again. And this is what people call a synchron algorithm. And it's called synchron algorithm because he's the one who proved that it converged. So again, the synchron algorithm would be just simply, just give me any initial guess for V, and you just do this like this. So U receives A divided by KV, V receives B divided by K transpose U. And the nice thing about it is that it's very easy to monitor the convergence. Okay, when U and V stop moving, then you have converged. And maybe most importantly, it's very easy to implement. It's 3 lines of code, you know, compared to this 1,000 lines of code that I was showing to you. And the third important thing is that if you think about what is the computational effort that is involved here, it's mostly about multiplying a kernel matrix times a vector. So this is very easy to parallelize, very easy to run on GPUs. And actually, there are some particular cases where applying a kernel matrix times a vector can be even speed up. It's a very well-known field. And so we are trying, you can try all sorts of tricks to even make this a bit faster. But in the baseline implementation is essentially a kernel matrix times vector multiply. So when I present it this way, the synchron algorithm might look a bit magical. You know, I showed you a few things. For those of you who are familiar with optimization, there's a far, I think, more powerful way to look at it, which is to consider the dual problem that corresponds to this entropy regularized problem. So if I take the dual, for a second, please forget about the right-hand part and this right-hand part here, and just focus on the left side. Remember, I told you that the primal problem in transport had a dual that looked like this. There were some constraints on alpha and beta, but it was basically looking like this. Where it turns out that when you add this entropic regularization on the primal, there's no longer any constraints on the dual variables, and this only becomes some kind of regularizer here. And so this is, the regularized problem is convex problem. The regularized dual becomes a concave maximization problem. And so it's actually very easy. And then what happens is that for those of you who know about optimization, you know that when you have an unconstrained problem, it's usually much easier than when you have a constrained problem. And so in that sense, it's very easy to think about trivial updates to this unconstrained problem. And one of the easiest ways to look at this is to do what people call block coordinate ascent. Block coordinate ascent simply means updating alpha. So it's as if you were saying beta is fixed. You update alpha to get the best alpha. And if you do that, if you cancel the gradient with respect to alpha of this energy, you get this update. And if you cancel the gradient with respect to beta of this energy, you get this update. And actually, this is exactly like doing the synchron algorithm. So in other words, the synchron algorithm is just a block coordinate ascent scheme on the dual problem. I would like to, in OTJAX, we have all sorts of variants of the synchron algorithm that are implemented, but if you understood this, this was the main point. Now, I would like to briefly mention the differentiability of what I just proposed, or more generally of the Wasserstein distance. Suppose I have this configuration, you know, blue points and red points, and I basically either run the linear program or I run the synchron algorithm. But what I would like to understand is a local perturbation, an idea of what happens when I perturb locally my inputs. So by perturbing locally the inputs, I mean what happens when I change the weights, of this measure. Or similarly, what happens when I change the locations of the measure. So this was going in the sense of your question earlier on. It's basically if I have, I just made the effort of computing Wasserstein distance. If I want to make it smaller, what are my leverages basically? What should I be pushing to make it smaller? And I can either change the location, of the factories or of the mines, or tune a bit their production. And this is important because maybe some of you might have heard about, for instance, Wasserstein GANs or other models where we are trying to produce something and use Wasserstein distances as a loss. In that case, really, this is what you want to be able to figure out. So it turns out that in both cases, it's actually quite simple to compute those two gradients because one can use what people call the Danskin approximation. So I have a slide on Danskin, but I think I would be short on time if I present it, so I removed it. But essentially, what the Danskin approximation says is run the optimization that you need to compute the Wasserstein distance between those weighted point clouds. You get either P star or alpha star, beta star, the dual variables, and just pretend that they're fixed now. They don't depend on the data anymore. They're just frozen. And now just simply evaluate, your objective with respect to the gradient of the objective with respect to the moving parts. So let me just try to provide an illustration of how this might work. Okay, imagine right now, I'm using the linear programming formulation. I might be using Synchron later. It would be the same. Imagine right now my data is as follows. X and Y are given, A and B are given. Imagine I am going to perturb a little bit the X's, the locations. What you can see is just like what I did in the previous plot, nothing has really changed in terms of the P star. The P star is still locally the same. What happens to my objective function at this perturbed solution is, the P star is now computed at x plus delta x by, but I just saw here visually that this P star has not changed. What has changed, however, is the distances. The distances from x plus delta x to y are not the same as the distances from x to y. So there's going to be a notion of, if I want to talk, the Jacobian of the distance matrix is what would be of interest here. So in this case, this is what really Danskin approximation means. It just means just run your solver and then pretend that this is not changing, this P star is not changing. And so you can differentiate your Wasserstein distance with respect to any parameter. This could be parameterized with respect to the weights, X, or actually, and this is probably what a lot of people are doing. So for instance, I've seen in a lot of self-supervised works, like Suave and other papers, they are trying to essentially parameterize costs, and they're going to differentiate this Wasserstein distance with respect to the cost, but essentially the cost changes here, but the P star is kept frozen. So this is when you want to differentiate the Wasserstein distance. Okay, so in the case where what you're interested in is really computing a distance. What happens if you want to differentiate the optimal matching coupling? For some reason, you want to understand how the optimal matching P star changes with respect to data. So here, it's a bit like differentiating the minimum value versus differentiating the R-min, and we know there are a few issues there. What you've just seen here in this plot is that, of course, P star is not changing at all with respect to the inputs. So in other words, if I wanted to write what the P star, how the P star is moving here with respect to the x's or the cost parameters, what you can see very clearly is that it's either 0, P star is not moving at all, or it's infinite in the sense that I didn't show it here, but it jumped to a completely different assignment. I think it's very easy to visualize this, even with the optimal permutation. It's very easy to think, for instance, that if I have my square scenario like this. Suppose the blues are well positioned in their corners. If I am, let's say, here and here, like this, then it's pretty clear that the optimal matching is going to be this, okay? But then, and it's going to stay like this for a while, if I move a bit my points. But all of a sudden, if I'm cross like this, if I'm moving a bit my particles like this, all of a sudden it will switch from that matching to, let me see if I have to this one. And this is what I mean by either it doesn't change or it makes an infinite jump. I have changed infinitesimally the points here, but the jump is very large. And so this is how we also use the synchron algorithm in some applications, and we would like to use the synchron algorithm in some applications. And the way we do this is by saying, well, what about the P gamma that I showed you earlier? This optimal coupling that I get with the regularization. Well, I'm just going to first give you the picture, and then I'm going to explain how we do this mathematically. The first thing that you can obviously see is that if this is a P gamma which is regularized, it's going to move smoothly with respect to the inputs. And so the good thing about this synchron approximation is that it's going to have some interesting notion of differentiability with respect to inputs. So if you're using an intermediate matching step in your end-to-end learning pipeline, at least mathematically, we know that this is going to be moving smoothly because, again, P gamma is this unique solution of a convex problem. You can look at the all sorts of Lipschitz constants of the map that associates those quantities to this P gamma. Now, there are two ways to do this. I will be a bit brief because I want to cover the other part. The first one, I'm guessing that if I ask anyone in the room, how do you differentiate something with respect to something? You just say, I don't think about it. I just run my PyTorch or TensorFlow or JAX and ask it to differentiate things automatically. And I trust it to do it intelligently. And this is actually true in this case, because of course in the synchron algorithm, if you think about it, it's a very simple computational graph. You just start with, let's say, an arbitrary value for the vectors and just apply those updates as many times as you want. So you can see it's like a stack of operations. And then you can think, this is my solution after peak L iterations. It's very easy to compute the Jacobian of this matrix with respect to either X or A. And it's going to be easier to compute the gradient of anything that involves PL with respect to X or A using reverse mode differentiation. So that's the naive part. I would say that there is another part, but I want to be a bit brief because I want to keep more time for the rest. But I think it's an interesting thing to have on your map. Whenever you compute something which is the result of a fixed point iteration, either you do what I just described, which is unrolling the optimization algorithm, so the steps of the optimization algorithm, or you do something called implicit differentiation. So the advantages of unrolling the optimization algorithm is that what you're doing is more or less exact, but the disadvantage is that you need to store all of the intermediate steps of your fixed point algorithm in memory. And so this can be costly. There are ways to mitigate this using checkpointing, but in general, people try to avoid this, and the community is interested a lot in this idea of implicit differentiation. So what is implicit differentiation in a nutshell? Implicit differentiation is the knowledge that the result of your fixed point iteration of this optimization satisfies some properties, and that if you were to perturb the inputs, your new solution would still satisfy those properties. And therefore, you can predict, you can use that to compute the Jacobians of your solution with respect to the inputs. So let me try to explain this in a nutshell. In optimal transport, what I just tried to explain is that it's essentially when you're doing regularization with a synchron algorithm, it's about solving this unconstrained dual problem. And what the unconstrained dual problem does is it tries to maximize two vectors alpha and beta given all the rest. Okay, the rest is the descriptions of the points, maybe the cost function, maybe gamma, the value of your regularization. So what it does is, this is the data, this is the variables, this is the objective, and what I know is that I have converged, I have maximized this problem when the gradient of this energy with respect to alpha is 0, and when the gradient with respect to beta of this energy is equal to 0. This gradient is actually given in analytic form. It's those two equations, but don't pay too much attention to those equations. What I will basically be using is this relationship. When I have the inputs and the variables, and I define this vector valued map H, which takes for everything here the gradient with respect to alpha of the energy at that point alpha, I know that I have converged, that I have found the alpha star and beta star that correspond to that data, if this here is equal to 0. Okay? This is by definition of optimizing this problem. So what you know, in other words, so those are the values of those gradients. Okay? What I know is that I have a function or an algorithm, this is synchron, that takes inputs and outputs two vectors, alpha star and beta star, which are those optimal dual variables. And I know that I have something to control given the inputs, the optimality of two variables, alpha and beta. So if I plug this into this, I know that there is an equation that binds together my optimization algorithm and its optimization, its first order conditions, basically. The fact that the alpha star, beta star are indeed optimal for this problem is that this must be equal to 0. So if I evaluate H with my inputs at their optimum, this should be equal to 0 no matter what. And so implicit differentiation is essentially about perturbing mu and nu, or C, or whatever you want, at the point where you start with 0, and then compute the Jacobians of this. So I'm sorry, this is a bit fast, but I want you to have this on your map. The map is to say that the Jacobian of the function f of those outputs here, with respect to any variable, is going to be given to you by this operator. And this operator here is a linear system. It's the Jacobian, the inverse of this Jacobian of this map with respect to alpha beta. So it's going to be differentiating this map with respect to alpha beta up at the point that you want at the input and evaluated at alpha star b star, inverse the Jacobian of this thing. So just at the higher level, the matrix that tells me how the solution to the optimal transport problem changed with respect to one input is given to me by inverting this operator and multiplying by this. Thankfully, in practice, we never really need to compute those Jacobians. I mean, we don't need to compute them in a sense, we don't need to materialize them. The only reason we want to have access to those Jacobians is because typically what I want to do is define some, in machine learning, we're always in the end pulling together our huge end-to-end differential pipeline, whether it's an LLM or whatever. It's going to be like, no matter how many transformers you're piling up, in the end, you're always estimating all of those parameters with just one real valued loss. And so what you want to compute is the gradient of that real valued loss with respect to all of the parameters that you've had before. And so if you're plugging, let's say, optimal transport and your optimal coupling matrix inside an architecture, in the end, you will still estimate the parameters of that architecture using gradient-based optimization because you only have one loss. And so you never really need to compute the Jacobian of transport with respect to some input. You always need to apply the Jacobians transposed to a vector. So this is called VGP. So if you're not familiar with GVP and VGP, this is I really highly recommend that you look into this. This is the mathematical way of proving, of explaining backpropagation. So if in your deep learning classes you've gone through backpropagation, but you haven't encountered or heard about VGP or JVP, I recommend that you go back, and try to find a clean resource that helps you understand this, because this is, to me, fundamental, in deep learning. So in deep learning, the only thing that we want to find, have access to, is being able to apply the transpose of the Jacobian of something of interest to any arbitrary vector z, and that arbitrary vector z will be given to you by reverse mode differentiation. So in other words, the only thing that matters is not materializing this huge matrix. It's being able to apply its transpose to a vector. If my huge matrix was this, well, the application of this huge matrix transposed to a vector becomes this thing. And here's the magic. Those operators are given to you directly by JAX. So you just specify h. My function h was analytical. It was very simple. JAX will directly instantiate this. JAX will directly help you solve a linear system with that operator without materializing a matrix. This is important. Everything here is functional. We are never going to materialize matrices that are huge. And this is basically the VGP of the other operator here. So in summary, you can now, for instance, compute the Hessians of the Wasserstein distance, which cannot be computed using Danskin. You can differentiate optimal transport automatically using OddJAX. All of this implicit differentiation pipeline is implemented in our toolbox. So if you want to be creative with matchings and optimal matchings, etc., beyond Wasserstein distances, this basically allows you to do it without thinking too much. Of course, because there are numerical instabilities that might arise of this linear system, you should be a bit careful, but if you have an issue, please come to me. So now let me just try to close this sample-based approach and switch to the continuous regime by just presenting quickly the recent extensions that I think have made the field more flexible, those tools more flexible. The first one is the so-called unbalanced optimal transport extension. So you remember in the beginning of the class, it was very binary. It was either mass conservation, every blue point gets to meet its red point. Every blue point gets married to a red point, and we have those pairings like this, or the world of nearest neighbor, assignments when multiple red points can be assigned to only one blue point. It seems too much like a binary choice. Either you do full bijective or whatever. Maybe all of the red points collapse to one blue point, and that's not a problem. So one of the ways to parameterize this is to take a look again at this model and think about, what does it mean to have P that has row sum equal to A and column sum equal to B? Well, you could think about this as dualizing. People call this dualizing the constraint, which means you add a multiplier here, which is rho, just a real value, and you penalize the KL Kullback library divergence from this row sum to A and column sum to B. So here, intuitively, you can see very clearly that if rho goes to infinity, essentially, I'm back to this equation. Because if rho goes to infinity, I'm minimizing over matrices P that have non-negative values, like this. But all of this block here goes to plus infinity if I don't satisfy exactly the constraints, right? So this is enforcing the constraint by letting rho goes to infinity. Now, if I leave myself some room for a mistake, and I allow P not to have exactly marginal A or not to have exactly marginal B, then maybe this yields a different problem, which is less constrained. And the great thing about it is that if you add an entropic regularization, a gamma entropic regularization to this, a few folks have shown that actually you can solve this with some kind of generalized synchron algorithm. So in other words, you can find more wiggle room, and do what people would call also partial optimal transport, where the matrix P here will not necessarily have, the intended marginal. And you can also have a different constant rho for the first marginal, a different constant rho A and rho B. Yes?
Is there any intuition on why we use the KL divergence here? It seems like a very unnatural metric, because I would think about like an L2 norm between P1M and A to be more intuitive in this case.
So I think one can argue about this. I personally don't like the L2 norm on probability distributions, because usually, there's lots of literature that tells you that it's not it's not a good notion of distance between histograms or like counts. So maybe in 20 seconds, imagine I have a text that mentions 0 times tennis, a text that mentions tennis once, and a text that mentions tennis twice. Okay? So if you think about Euclidean distance between the word counts, 0 and 1 is at the same distance than 1 and 2. Okay? But from an information perspective, for me, the biggest gap is between 0 and 1 and not between 1 and 2. Because if you tell me that tennis was there once, it's already a huge, information as compared to being there 0. Whereas between 1 and 2, okay, maybe the person repeated tennis twice, but tennis was already there. So overall, it's very, there's a huge information theory, behind the fact that we want to use KL and not L2 for histograms. That being said, you can use L2 if you want. In this case, and especially in this work here, people have looked all sorts of regularizers, and what this involves is the Legendre transform of the regularizer. There's a few things. The one reason why I've put KL forward is that if you use KL here and then you regularize by entropy, by adding minus gamma times entropy of P, or generalized entropy, because here P is not necessarily summing to 1, you get this modified synchron algorithm, which is trivial to run. So in other words, if rho is infinite, you can see that essentially you have something that really looks like it's 1 divided by 1. So it's infinite divided by infinite, so this collapses to 1, so you recover the usual synchron algorithm. And if you have a row that is finite, then you kind of interpolate. So you have this kind of update. So I would say KL is simpler just for the same reason as entropy is simpler as a regularizer. But mathematically, at least on paper, you can use whatever you want. Even entropy is not necessarily the best strongly convex regularizer on the simplex. You can come up with other regularizer.
Okay, I see. I was looking at it as just a Lagrange multiplier of the constraint.
Ah, yeah. You're right.
But yeah, this makes sense.
Yeah. Okay, I now understand where you're coming from. Yes. But here the thing is that there is a bit of a geometry, which is natural here with respect to couplings, and KL would be a more natural way to realize the constraint. Now, for the other extension, so one of the nice things about this thing is that, there's been work on this. There's also faster algorithms than this simple synchron algorithms. This was proposed last year. And so I find that people in applications, although this adds a layer, and adds yet another hyperparameter, I have found that people actually can take advantage of this hyperparameter for their applications. So that, for instance, one of the benefits of this approach is that maybe this is able to discard some outliers in your data. So in a way, the story is like, I want to couple those 2 point clouds, but sometimes I'm okay dropping some points, either from the red set or the blue set. And you can also basically impose this constraint and let this one relax, or vice versa. So there's lots of semi-balanced, balanced, and balanced approaches out there. And so this I think answers this question of whether I want to use nearest neighbor assignments which don't conserve mass, or I want to go something that is completely conservation of mass. So in applications, I think this is useful. The other nice extension that was proposed in this one is a bit newer. It's this idea of, okay, I used to add entropy here to make things a bit better behaved, and I got quadratic time algorithms, but this is still very long. Is there something a bit faster than I can come up with? And so it turns out that there is another way, conceptually, of trying to get things to operate faster, which is to add a constraint on the rank of this matrix P. So by this, here I'm going to do this constructively. If I give you a matrix Q, which is row sum A and column sum G, so here I should probably say that G is in the simplex of size R. So R, okay, imagine N is 10,000, M is 10,000, R is 100. So if I come up with a matrix Q that has marginal A and G, and another that has marginal B and G, like a common marginal in the middle, and G is very small, then you can show that this matrix, Q, which is size N times R, times diagonal matrix of 1 over G, which is a small square matrix, times R transpose, which is this R times M matrix. R is M times R, so R transpose is going to be small r times M. Then this matrix, it's easy to see that this is actually satisfying the marginal constraints. Okay, so one possible approach to solving this problem then is to say, I will focus on low rank couplings. So there are going to be Q parameterized by QRG, so I have three variables now to keep track of. This is my coupling, and this is my distance. Okay. So of course, this is an N times M matrix, but because it's low rank, I can try to take advantage of this. So how do I take advantage of this? Well, the first thing you can notice is, of course, if I split those three variables into three updates, by doing alternate updates, I loop on Q, R, and G. Each of those problems actually becomes a bit simpler because this is a dot product between NM and NM matrices, but here there is a block of size R times M, which I can put on the other side. Okay, so it's going to be the same thing as doing like a mini optimal transport problem in a smaller set size, which is N times R, M times R, and this is just simply R. And the way I got to put Q, isolated here is just simply by flipping that part over to the right. And so, in a nutshell, the idea of this algorithm is to update each of those three blocks alternatively, and typically we will add some entropy to make things easier for each of those small blocks. And the one thing that I need to stress is that at each iteration, in principle, we need to recompute this distance matrix. It's like a virtual distance matrix. But the good thing is that if we assume that the cost matrix is low rank, so it can be written as A times B transpose with a small dimension. So typically when you use a squared Euclidean distance, if you have your if your matrix is xi minus yj squared, okay, then you can write this matrix. If I write, let's say, x tilde is equal to the vector of xi's, and y tilde is equal to the vector of the yj's squared, then basically you can write C is equal to x tilde times 1s of m plus y tilde, plus 1n times y tilde transpose minus 2x transpose y. Okay. So this is a first step in having a low rank decomposition. Then you have to write them like this. I mean, there's a way of doing it very simply. But what I just want to say is that your cost matrices here, they are actually, if you have a squared Euclidean distance, your cost matrix is low rank. It doesn't have low rank n or m. It will have rank d plus 2. And so if you're able to simplify this cost matrix, find an expression for this, then these multiplications here become essentially become linear in n. And then because the transport itself is handled with respect to n times r, and if you think that r is just fixed, then you can come up with a linear time algorithm to compute this. The caveat for this, though, is that this is not convex. Here we're doing alternate optimization. We're doing alternate optimization, and so we are not guaranteed to find the optimal matrices. So this is a bit like, for those of you who are familiar with this, it's like non-negative matrix factorization, for instance. We are trying to decompose something as a product of non-negative factors, but we don't have a convex algorithm to solve it. Let me try to give you a bit of an intuition and how this relates to entropic regularization. Well, it turns out that it's a bit related to entropic regularization because we are somewhat parameterizing a path of solutions that go from the simplest to something which is closer to the original solution. So maybe a bit counterintuitive, but let's move from right to left. So from right to left, when we use very small epsilon regularization parameter, we have essentially something that looks like this optimal transport matrix, which is very sparse. And then as epsilon increases, we get this blur, which is the product of the marginals. Well, the same thing is intuitively happening with our rank constraint matrices. With large rank, we get more or less something that looks like, it's as if you were computing small blocks, 100 small blocks to approximate this line. And then when the rank starts decreasing, we get again something that is very block-wise, coarse. And so in a different way, we get something that is coarse in both trajectories. But I think there is an interesting similarity. The good thing about this approach is that it's linear time. So again, with respect to R, so it's going to compute, in a way, we get even more speed up. In Synchron, the Synchron algorithm is known to converge much faster when epsilon is large, but here we don't even need to do quadratic time operations. And let me just briefly conclude on this part by saying that all of those, this low rank, solvers, favorable properties extend to the arguably much harder Gromov-Wasserstein problem. So remember the Gromov-Wasserstein problem was this idea. We had a quadratic energy for P, which in itself is actually very costly to even evaluate. The gradient of this quadratic energy with respect to P is equal to this quantity. And so this is a matrix NN times a matrix NM times a matrix MM. And so this is cubic time. Okay, this is going to be n square m plus, so it's going to be nm times n plus m. Even just evaluating this matrix products is actually very, very costly. So what we showed is that if the cost 1 is factorized as a low rank cost 2 as well, so imagine you have 2-point clouds and square Euclidean distances in each space, 2 different dimensions for square Euclidean distances, or you can come up with approximations for those matrices. We also do that in our software. Then essentially, this C1 times P times C2, if I am using a low rank solver for P, the previous iteration, remember, was this thing, was this Q times diagonal of G times RT. And the cost C1 and the cost C2 are on the left and right hand side. And it turns out that thanks to those decompositions, I can run the inner loop of this Gromov-Wasserstein thing by using a low rank cost that changes iteration after iteration. So it's a bit, maybe a bit complex to explain it in one slide, but it's just to say that all of the ingredients that you need to keep everything low rank are basically in place. And so you can now run Gromov-Wasserstein solvers using those low rank assumptions on cost and low rank assumptions on coupling matrices to hundreds of thousands of points. So in summary, what's going on a bit in terms of solvers is that if you want to solve the linear optimal transport problem, you can always use linear program. I definitely would not recommend it in most applications because I think this doesn't scale, doesn't have a GPU scaling. I mean, there is a GPU implementation of the Hungarian algorithm that I'm aware of in the Scenic toolbox by Google Research, but it's not going to scale. And it's unstable in the sense the P star is not very good. You can use entropic regularization. So this has been going on for about 10 years now. But it doesn't scale to lots of, I mean, maybe 20, 30,000 points is still okay, but after that it starts, start feeling the heat. And the GPU starts warming up. The low rank approach, which I've been describing, is not convex. This is the problem. You're still stuck with maybe tuning some parameters and making some choosing various initializations, a bit like in k-means. But it works quite well, and it's GPU friendly, and it works for larger scales. The Gromov-Wasserstein, and more generally the fused Gromov-Wasserstein problem, again, this is really not working well. I presented in the very beginning the quadratic, the entropic approach. It's basically quadratic or cubic, depending whether you make this assumption on the cost matrix. Whereas in our case, it's going to be linear, but not convex, again, GPU friendly, and this is what I just explained. And I just wanted to briefly highlight something that we just submitted to NeurIPS, which is the unbalanced case. Remember, I told you about unbalancedness. You can handle this with Synchron, this KL's terms that we were talking about. This works well with the linear problem, and this also works with the Gromov-Wasserstein problem. This was proposed also recently. And so what we recently proposed is unbalanced variants of this low-rank approach, which scale again to hundreds of thousands of points. And maybe the best, since this is a machine learning school for science, maybe the best demonstration that this actually, all of what I presented works, is in the very recent submission that we put on bioRxiv of this toolbox called MOSCOT, Multi-Omics Single Cell Optimal Transport, which is using in various ways, mappings or matchings, where we're trying to match in time and in space populations of cells. So for instance, an application of the fused Gromov-Wasserstein problem is the following. Imagine I have a slice, of a mouse brain. I can use single cell genomics to pick one cell in that exact location in space, look at the RNA-seq counts, so it's like a huge feature vector of counts. And so I have this kind of 2D map of features in high dimensions. And then I want to compare this slice maybe to the slice of another mouse in a later developmental process, or maybe seq or something like this, and try to map, basically try to understand what is the matching between those cells here and those cells here. And this has been typically done using this fused Gromov-Wasserstein approach. So why fused Gromov-Wasserstein? Again, because we're going to use 2D locations as distances on the space. So this is the two things that actually don't communicate. One is 2D and the other is 2D, but they are different references. And then we are going to look at RNA-seq as the common, fused term that appears here. And so all of the, if you're interested in using this, looking at this, so this MOSCOT toolbox has a lot of tutorials that explain basically how this can be used at large scales for genomics. In the background, all of this uses oddjacks. So all of the computations are done using our toolbox oddjacks, but this was a nice success story for us yes.
Do you think that this method could be used to somehow more trivial and down-to-earth task, like for example, image registration, when you have, I don't know, 2 slices, 2 biopsy slices with some cells which are slightly misaligned, but still we want to perform some matching with some metrics? Do you think it?
But so here the goal would just be registration of 2D point clouds?
Probably yes.
Yeah, I think you can view this as optimal transport, so you can clearly use it. We don't need to go into the machinery of using maybe the fused terms and the Gromov-Wasserstein aspects.
Yeah, but my point is that, for example, in those medical applications, usually sometimes cells are pretty deformed between certain images. So I don't know, but this is a point where I see that some introducing entropy or some sort of.
No, so for instance, if you have two 2D locations of things, and each of the things has its own features, and you want to do a matching, you can use this thing. Because you're going to compare basically the features you know, the two cells, the features, and then you use the locations on the 2D space as another, as the quadratic term here, basically.
Thank you.
And actually here, you probably don't use, you don't need to use Moscot to do that. It's simpler to use directly OT because we have a fused Gromov-Wasserstein solver for that. So before maybe going to the continuous part, I just want to recap a bit. We've used entropy, we've used low rank. Both entropy and low rank actually go against, you know, the dogma or the idea of linear programming, which is that this matrix should be sparse. It should not only be sparse, you know, for linear programs, but it's also full rank, you know. What I want to say is that if I look at these pictures, what lies here is the solution of the linear program. And I know that this is very low entropy, and I know that it is very high rank. Actually, it's going to be full rank. So the argument in both cases is not, let's try to recover the solution of linear programs by using those regularizations. Instead, it's really, we believe there must be some inductive bias, you know, that helps combat these instabilities and, you know, overfitting, and either rank or regularization helps. And it also helps computationally to go faster. I showed that this helps. Differentiability helps here. Differentiability here is more of an open subject we haven't really tamed. Okay, so now let me go to the continuous part. So I would like to give another motivation from science for this problem because I think it's an exciting one. And this is also from single-cell genomics. So one of the very exciting, you know, phases in personalized medicine that we're seeing now is that you can get a patient that has a disease, let's say cancer, do a biopsy, look at it, extract, let's say, a few thousands of cells of a tissue of interest, and we are at the point in time now that using single-cell, you know, sequencing, we are able to capture at any point in time, sorry, at one point in time, I should probably say, what is the activity of that cell at that point in time. So essentially, how much of each gene it is transcribing by counting RNA strands. And this gives us a very fine-grained, you know, idea of what the cell is undergoing. This gives us a very high-dimensional feature vector of, for each of the genes of interest, let's say about 35,000, what's going on in that cell. The problem, though, is that to get that data, we typically need to split, you know, the cell open, so we kill it. So once you have extracted cells, you know, you can get a picture of them, but you cannot put them back. Now, what we would like to understand is how do the remaining cells here react to some drug? And so what happens is you give a drug, you wait for a few hours, you will get this population of cells that has evolved with time, and you're going to sample another batch of cells that you're going to sacrifice in a way to get measurements. And the goal is to understand basically, using optimal transport, what is a likely action of the drug on the cell space. And to do so, what we will try to essentially do is say, okay, I had these cells in this configuration here. They died now because I just measured them. But the cells that remain are more or less statistically similar to the cells that were here. So for instance, let's say if half of them were cancer cells, and half of them were healthy, I picked a proportion that is more or less 50-50 as well. I apply the treatment, I'm also going to get the same proportions. And so those populations are actually representative of the underlying, you know, those samples are representative of the underlying populations, and I will try to guess. So one thing that's not exactly in this context, I should probably qualify it better, is that people started using optimal transport in these setups about 3 to 4 years ago. And there was a famous paper by Jeffrey Shibiger and other co-authors. They were not doing this for the treatment of drugs, but more like to study differentiation of cells. And what they did is quite intuitive. They said, okay, let's solve the matching problem. And it feels like this one is going there, this one is going there, etc. So I am in this space of genes, maybe PCA space to be a bit more rigorous. And I will try to fill in, you know, that question using, using the optimal matching problem. And to be fair, what Schibinger and co-authors did was using the sinkhorn approaches that I described, using also a bit of unbalanced constraints so that some of the cells could die and some of the cells could be born. So this is very much, related to the solvers that I just described earlier. But what people want to know now, and I think it's a more exciting project or idea, is maybe rather than actually focusing on this sample-to-sample map, can I try to learn a function that is associated with my drug? So here the idea, if you want, is to say a drug, hopefully, does not act in the same way on cancer cells that it acts on healthy cells. And maybe even, within the healthy cells, maybe some of them will be impacted differently than others, depending on where they are in this space. So we want to be able to fill up, this space with a lot of arrows that are explaining what is the action of the drug, depending on where you are in the space of cells. So this is a fairly crude model, but it's more advanced than the one where you just try to reconstruct one-to-one matchings. So to do this, I will need some tools of continuous optimal transport. Yes? Yes?
What are actually what is the mapping between green and yellow cells? I mean, the yellow cells are the predicted states, similar states of.
No, so here both are observations.
Okay.
I just sampled. So I took. If I go back here, I took cells in their original state, like in control state, you could call it. This is a sample of my cells. I apply something, so I know something is going on, in those cells, and this is reflecting the fact that they're going to change. I sample again cells after the change, and now
they are the same cells.
No, they're not. I mean, they cannot be the same for the reason that here, when I put them here on the right-hand side of the picture, I'm killing them because I need to compute those features. So I split open, I count RNA strands, and I get some counts, 35,000 counts for each cell. But these cells, I cannot put them back. I cannot tag them, tag them, look at what is inside, close them again, put them back, and then later on, see what happened. So I don't have matched pairs, if you want. The only thing that I have is basically another fresh batch of cells. So of course, those cells were somewhere inside in the first biopsy, but I didn't observe them. I'm observing now after the effect, and then I'm trying to.
And the metric here is the similarity of features, right? You are trying to find as similar cells in this new group as possible, right?
Yeah. So the cost that we're going to use to score how far this is can be the square Euclidean distance. It can be other things. I will explain a bit later.
Okay.
So this one, so imagine I have this raw source, my measure source and my measure target. In the very first slides, I think I explained this, how this Morse problem. I'm trying to find a map that acts on the source and gets the target, and I want it to be thrifty, in the sense that it's going to save on displacements, but still recover the target measure. So this is what, so far, I think this is the only element of continuous, formulation of transport that I gave you. And then I give you two other blocks, which are discrete. And the blocks that are discrete is the following. I have two discrete measures, points X and weights A and B. I have this n times n matrix. And the other one was this dual formulation, which I have weights, price vectors alpha, price vectors beta, constraints that alpha I plus beta j is smaller than xi y j, and this is the objective. Now let's think about what happens when n and m go to infinity. So when n and m go to infinity, essentially what you will have is an infinite matrix, which is a coupling density. And the coupling density needs to satisfy marginal constraints. And when n and m go to infinity, essentially I will have a vector alpha I for every point. So this becomes a function, and beta becomes a function. So the very natural extensions, direct extensions of those two objects that we've been manipulating a lot of times are computing a coupling density between two probability distributions. And the cost here, this was just Pij times xiyj. This is going to be just the integral, the double integral, over x, of the cost over x and y integrated over the coupling. And same thing for here, for the dual problem. Rather than having alpha I at each point xi, I'm just going to define a function f that I integrate against the first measure, and the function g that I integrate against the second measure. Okay? So this is what we will now need to prove this Brownian theorem. We will need to play with those infinite dimensional linear programs. So what I said for the primal problem remains. This problem is a primal, this is a dual, and those solutions in optimization, they always have a link. The solution of the best coupling and the solution of the best dual variables have something that helps me put them together. So let me try to summarize in 3 slides, probably maybe one of the core of optimal transport theory. So the first thing is, this is going to be a bit of a game. I am going to look back at this problem, okay? I'm going to look at a function f, function g, that I integrate over rho s and rho t, and I have all my interest here is making f and g as large as possible because I'm computing the soup, but I have a constraint, which is that for every x and y, f of x plus g of y needs to be smaller than x, the cost between x and y. Okay, so those are my, now it's not my cost vectors or like the price vectors, it's my price functions. So if you were to solve this, imagine I am solving for you half of it, and I'm telling you f, you cannot touch it. Okay, there's 2 variables f and g, and I'm telling you f is frozen. What can you do about g? What is the best g that you can come up with? So here, if you look at this optimization problem, of course, your interest, again, is to make g as large as possible. Because we're trying to find g that maximizes this. I'm integrating g over a measure, which is positive. So the bigger g is, the happier I am. So this goes back a bit, to the idea with the Poland Post Service trying to set prices. I want this to be large. But the one thing that I cannot do, though, is I cannot make g so large that this is no longer insured. So my goal is to make g as large as possible, but I know that for every point x and y, so for a given point y, I know that for every x, this needs to be valid, which means that g of y, no matter what I do, if I want to have a solution that is feasible here, needs to be smaller than the cos xy minus f of x, which means, in particular, that needs to be smaller. If it has to be smaller than a lot of things, it's the same thing as saying that it has to be smaller than the smallest of those things, okay? If I want this to be true for every x, in particular, it's the same thing as saying that it has to be true for the smallest x, for the x such that this is smallest. So in other words, I want g to be very large, but g at every point y cannot be bigger than this thing. So what is the best possible g that I can come up with given a function f? Yes? It's this. Exactly, it's this. It's this if given x of cxy minus f of x. Great thing is that, of course, this definition only depends on f. Okay? So in a way, you give me a red function, I can come up with a blue function that is the best possible. There's no better choice for this because it's saturating the constraints that I give it to, and I want it to be big no matter what. So people call this the C transform, like turning a red function into a blue function. Now, it's very easy to do the other way around. If I give you a function g, what is the best red function? It's going to be inf of y of c of xy minus g of y, okay? So this is what people call C transforms. And the vocabulary, the jargon extends a little bit, because we say that a function f is C concave if there exists another g such that f is equal to g blue bar. So this is just to say that whenever you're doing this game of turning a red function into a blue function and a blue function into a red function, you're improving the objective. And so you might as well start with a function that is already the red transform of a blue function. And so this means that if you're giving me the best possible solution, f star, if I just do this game of turning it into a blue and then turning it into red again, in principle, I know that this f star has to be itself the transform, the blue transform of the red transform of a blue function. This is a bit of a technical point. We will discuss it a bit later. Now here is the Brognier, the Gangbo, McCann, Brognier, important theorem in optimal transport. This is quite magical because it links this function in the dual problem, which seemed to be something that you should be able to achieve. It's not so horrible, an optimization problem. With this one, which is horrible. This problem is really horrible. It's not even a convex constraint. It's really bad. So the theorem is as follows. It says the following. It says, if I am able to compute the optimal dual function, the optimal transport is necessarily this expression. So let me try to prove the expression so that I can parse it out. So the first thing the first step in this proof is the following. If I have a coupling, remember the couplings are things of this form. Okay, so I have, let's say, this is my 1D, another distribution, and this is going to be my coupling here. Okay, so this is going to be my P star. I am going to assume that there is one point x0 and a point y0 for which the coupling is positive. Okay, so this means that some mass of x0 is transported to y0. Okay, that's the only thing that I'm assuming. And it turns out, I think you can turn off it. It turns out, this is a very famous result of duality. If the solution at one point in the coupling is positive, then the constraints are saturated at that point in the dual problem. Remember what the dual problem was about? It was saying f of x plus g of y is smaller than c of xy. If at some point p, basically this is positive, then basically mathematically this has got to be equal at that point. This is primal dual relationships in linear programs. You have to believe me here because this is very, very standard. So if this is true, then we have this, okay? Now, I told you that even if you gave me an f star and a g star, I can actually improve, or maybe just change nothing, things by considering the blue transform of this f star function. Okay? So I'm going to do this. I'm just saying, okay, maybe you gave me a pair f star, g star, but it turns out that getting the blue transform of g star of f star is not going to make things worse. So this means in particular that if this is observed, then we have this I have this equality here. Okay? Now remember what is the definition of the blue transform of a red function? The definition is that f star blue transform at y0 should be equal to the inf, here I'm using the notation z, but it's basically any x, of any z computing the cos of z y0 minus f star of z. Okay? So if I reconcile those two things, I'm telling you something is equal to this, but this something should also be equal to the inf over z's of this. This means that x0 is a minimizer or a critical point of this energy. So if this x0 is a minimizer of this energy, it means that the gradient with respect to the first variable of the cost computed at x0, y0, minus the gradient of star x0 is equal to 0. In other words, this here is equal to this. Okay? Now, the part where I didn't make the assumption very clear, gradient of 1cx is a function with respect to y0. And if this function is invertible, so people call this a twist condition, if this function is invertible, then I get that I can invert, if you want, this function and apply it on the other side. So this is the function which to anything associates gradient of 1cx computed on that anything. If this map is injective, then I can compute this. And this basically tells me that whenever there is a pair x0, y0 on which there is a mass, I know deterministically where x0 is sent to, and that is y0, which is equal to this. So in other words, there's no, let's say if I was looking at the slice of the coupling on x0, it could have been something like this. You know, it could have been a probability distribution because the coupling is probability distribution, just in the case where we have, you know, those blurry things. But it turns out that it's not. If you give me an x0, I know that there's only one point y0 that where x0 is going to land. And this is my transport. This is where I have transported the point. Now, this is the most general result you will see in optimal transport. I mean, there's more general ones actually for Riemannian manifolds and things like that. But for the RD case, this is the most general one. But you need to have a lot of things that are combined. Basically, you need to be able to compute f star. You need to compute this gradient of the inverse map of the gradient. So let's try to find simpler cases because this is a bit too generic. Suppose the cost is now a translation invariant cost, which is very classic. You know, it's like the square Euclidean distance between two vectors. Then let's try to see what happens. So let's say cost is xy. It's h evaluated at the difference of x and y, where h is convex. Okay. So square Euclidean distance is exactly that. Then this means that the gradient with respect to the first variable of the cost is equal to the gradient of h evaluated at x minus y. Which means that if I look at this, you know, mapping that I want to invert, it's basically the gradient of h applied to x minus dot, which means that if I look at the inverse mapping of this, you will get x minus grad h inverse applied on the thing. This is very easy to see. Basically, if I just, for instance, if I give you, let's say, grad of h of x minus y, is equal to z, okay? This is the same thing as x minus y is equal to grad h inverse applied to z. And so this is the same thing as saying that y is equal to x minus grad h minus 1 applied to z. Okay, so this is really just what I wrote there. Which means that the transport now is just given by this quantity. And maybe for those of you who know a bit about convex analysis, the inverse map of the gradient of a convex function is the gradient of the Legendre transform of the convex conjugate of h. So the convex conjugate is this thing here. It turns out that this gradient is basically this grad h minus 1 is equal to this grad h star. So most general result, general cost function. Translation invariant cost, we have this thing. Now let's go to the simplest case. H is the square Euclidean distance, or like the half the square Euclidean distance. In that case, it's known that the grad h is equal to the grad h star is equal to identity. And so we get basically this result. All of this disappears. So the optimal transport is x minus grad f star of x. This itself is equal to the gradient of the squared Euclidean norm minus f star. And it turns out that if f star is C concave for this cost, you can show that this is a convex potential. In other words, the optimal transport is going to be the gradient of a convex function applied to x. So this is the Brognier theorem. So the proof was done with, without being very rigorous in terms of, existence, etc. But this is roughly the mechanics of this. So this is basically what gives you the optimal transport in all situations. So let me try to wrap up very quickly now in the last minutes how this can be used. Well, now we still have this in mind, okay? So what people have done is they have used PCA to project those cells and try to compute the optimal transport in that subspace, okay? It's the first step towards this. And so what Charlotte Boone and other, getting inspiration from the other works by Makuva and Cortin did, is to say, okay, let's parameterize my transport as the gradient of convex potential. And I know that this convex potential, I'm here reorganizing a bit terms, has got to be the minimizer of this this slightly modified dual problem with the Legendre transform of F. So I'm going to use those input convex neural networks to parameterize convex functions. So what is an input convex neural network? It's a neural network that has the following architecture. It's basically going to take X as an input, compute an affine transform of X, and add a hidden vector here to this affine transform, and do this over and over again. Okay, so it's really a composition of this mechanism where I am computing an affine transform of X and adding basically a hidden state over and over again. It turns out that if, in the last layer, I'm collapsing everything. So in the last layer, this is the dot product and not a matrix, and this is the same dot product, not a matrix. It turns out that if all of those matrices have non-negative weights, and if all of the activations are increasing convex, so typically this is like soft plus, etc., then this is going to be a convex function of the input by design. You can show it quite easily. Essentially what you're doing is you're computing a fine transform of X. Those are all convex functions. And you are mixing non-negative combinations of convex functions, and you're reinjecting them one after the other. And so what you can try to do is try to solve this by parameterizing this f theta in the input convex neural network. The problem is that you have this Legendre transform or convex conjugate here that appears. And so what people have done is to use some kind of surrogate function for the Legendre transform. And so this leads to a few challenges that can be worked around. We have implemented it in NotJax, but to be fair, anytime you're optimizing over neural networks with constraints, remember here we have non-negative constraints, things can get a bit choppy. And the fact that we are approximating this Legendre transform with surrogate functions also are a bit of an issue. So I'm going to maybe very quickly conclude on another easier alternative that we've been exploring recently. We're going back to the more sophisticated model of, any H function. Remember that if I want to compute optimal transport using those math, in theory, what this tells me is that the only thing I need to have access to is a good approximation of this dual potential function. And it's actually very easy to get it using the synchron algorithm. So here I'm trying to mix a bit the continuous and the discrete world. I just run synchron on samples, so x1 to xn and y1 to am. I get pointwise estimates where my alpha I and beta j's, and I can come up easily with an estimator for this f star. And then what I just do is I just plug this f star into this machinery, and I get an estimator for an optimal transport. So I'm going to close a bit because I just ran out of time. Thank you so much for all of your questions. But this was just to explain that we can now start computing optimal transport maps for costs that are not necessarily only squared Euclidean distance, but have some structure. So there's a lot of I think promising direction in that sense. And we have another submission. So those are actually, I'm really closing on two accepted papers at ICML 23. So if you're interested in looking at them, please don't hesitate to come to me, ask me questions. It's more creative ways and I think more stable ways to compute maps that work better, in my opinion, than input convex neural networks because they're easier to tune, or they have some nicer properties than input convex neural networks. So I'm going to conclude here. So on the one hand, we have those sample-based discrete optimal transport solvers. I think we have made a lot of progress in these recent years to have very stable implementations now, and so I hope you can use them in your applications if you want to be a bit creative. They're very well studied, and so there's lots of things that I didn't talk about today. In particular, there's a very nice notion of difference between measures, which is called the synchron divergence, which is trying to mix a bit MMD and synchron distances. But so here I'm seeing really a lot of potential applications and the field maturing into being like a numerical library rather than an active research area. In continuous optimal transport, there's a lot of more open questions, in my opinion. I've showed you. I'm sorry if this was a bit too much to digest in a few minutes, but you can see that there's beautiful maths, going on there, linking various objects, dual potentials, and direct ways to estimate Monge maps. We can use neural networks to exploit these routes, but there are other approaches that are also popular. And in particular, I wanted to also mention links between diffusion models and a notion of optimal transport, which is actually one that leverages stochastic path, rather than taking the straight lines, that I showed you in the beginning, and thinking that straight lines are just the fundamental model. There are now well-known links to Schrödinger bridges, which study diffusion models. In all of those cases, my goal and that of our team is to make it easier to compute with odd jacks, so that in science, people can readily use this as a tool, and not so much, as a topic of interest on its own. Thank you very much.
Marco, many thanks for your amazing talk and giving us a deep dive into optimal transportation problem. And all of you, we invite for the lunch, and we'll see here in an hour. Thank you.